Okay, welcome again to this last day of the EDBT Summer School of Data Management and AI. Our lecturer today is Xiong. Her talk is titled Data Privacy in the Age of AI and Generative LLM Attacks and Defenses. And Lee is a Samuel Candler Professor at the Computer Science and Biomedical Informatics department at Emory University. She has a PhD from Georgia Institute of Technology, an MSc from Johns Hopkins University, and an MS from the University of Science and Technology of China. Her research is in the area of privacy enhancing data-driven AI solutions for healthcare, public health, and spatial intelligence. She's a recognized IEEE Fellow, an AAS Fellow, for her contributions to privacy, preserving and secure data sharing. And it fits well with the program, the topic of privacy. Lee, welcome.
Thank you, Dimitri, for the invitation and really nice organized summer school. Thank you all for showing up after the relaxing day on the beach. So you've learned in the past few days. I think in the past few days, you've learned about various applications and theory about the AI and data management. So today, the focus will be a little bit different. We're going to look at some of the potential privacy vulnerabilities and then the privacy defenses or the privacy enhancing technology so that we can build these AI solutions with privacy enhancement. So this is intended as a kind of introduction of the basic concepts and then also survey of some of the representative and state-of-art techniques. So this will give you a foundation if you're interested in explore this topic in depth, or even if you're not working on this area, working on this topic, when you're building your own AI solutions or data management solutions, you'll get a good understanding and awareness of the potential privacy vulnerabilities and the kind of techniques that can enhance your solution. So in the middle of the lecture, please feel free to stop me or any questions, comments, please, we want this to be interactive. So before we start, just a quick word about Emory University, where I'm from. It's in Atlanta, Georgia, United States. If you are interested in doing any kind of visit, short-term, long-term visit, you are always welcome. I would love to host you on that. So this is my lab. We work on kind of in general, the umbrella of trustworthy AI, in particular, looking at the trustworthiness, like adversarial robustness and privacy enhancing aspects, and also their applications for healthcare and public health and spatial intelligence. So again, if you are interested, please feel free to talk to me or get in contact anytime. So here's the outline for today's lecture. We are all going to mainly focus on the privacy issues in the kind of AI and LLM models, and it will be divided into two main parts. So the first lecture before the break will be focusing on the attacks, kind of the vulnerabilities and risks. And then after break, we'll look at the defenses, right? What are the potential techniques and solutions we can use to enhance the privacy? And towards the end, we'll introduce some open challenges. Of course, throughout the lecture, we're also going to discuss the open challenges and research directions and so on. So for the privacy attacks, here's a very brief outline. We're going to give you an overview of what are the privacy attacks associated with AI models. And then we're going to in-depth of the membership inference attack, which is a foundational attack for many other different attacks and have many different usages, not just to doing attack, but also for privacy auditing and so on and so forth. And then finally, I'll introduce, if time allows, we'll introduce a recent work that we have done. It's like a backdoor MIA or backdoor membership inference attack is a more powerful MIA. So that was the plan for the privacy attack. Okay. Any questions before we get started? All right, so we know that the bigger the data, the smarter the AI, right? We've learned probably over the years and then in the past week. But the flip side of this is that the smarter the AI, the more data it actually memorizes. And the data, what we mean by data here is the data that's used to train the models, right? So here we can see this is a typical AI pipeline. We have some data that belongs to private domain. This could be user data. This could be like electronic health records and so on. And then we have a model builder or model trainer pre-process and stores the data and trains a model. And then this model may be released as an API service, right? So we can query the API, get some model predictions and so on, and do decision making and so on. So now what we are actually looking at here is, if we have this API access, right? If it in the hands of some adversary or curious minds, they can actually use the API to try to infer about the original private data that's used to train a model, even without access of the training data. So that's the main privacy vulnerabilities we're talking about here. And why is this possible? It's because these models actually can memorize these training data. Right? These training data are used to train a model. The models maybe learn some general patterns, but they actually they could memorize some of these sample-specific data. And that's what we can leverage, or what the attackers can leverage to try to infer about the original data. So here are some basic attacks or well-known representative attacks, including membership inference attack or feature extraction attack and data extraction attack. In these days, when we are working with generative LLMs, we can actually extract exact training data verbatim that's used to train the LLMs. So I will show you some of these attacks, and in particular, the membership inference attack in depth. So here, before we talk about any attacks, we want to talk about threat model first, right? What adversaries know? What access do they have? So we usually talk about two kinds of adversary models. One is black box, one is white box. So for black box, we just assume the adversary has very little knowledge about the model. So in this case, they just have the API access. Maybe they have the confidence, the knowledge about the confidence output or probability output of the model, but they don't know about the internals of the model, right? The model is like a black box to them. So they don't know the model parameter, they don't know the model architecture and so on. So that's the black box access. That's a usual access adversarial model that we're dealing with. And then if we assume a stronger, more powerful adversary, then it could have white box access. In this case, the adversary actually knows about the internal of the model, like model parameters and so on, in addition to the input-output of the model. Right? So in this case, the adversary is stronger. And actually, there is techniques in the kind of security community where when the attack is designed in the white box scenario, we can always transfer it to a black box scenario. Because the common technique is that the attacker can actually build a shadow model based on whatever black box model and build a shadow model, then an attacker will know the internals of the model. And then we can actually dealing with it as a white box attack. So just to kind of transfer it from the black box to white box. Of course, the shadow model may not be exactly the same as the real target model that we're trying to attack, but then there is still, we can get fairly close to a white box attack. Okay. So with these two basic assumptions, later on, when we talk about different attacks, we will first kind of assume, okay, this is what kind of access capability we are assuming, and then this is what the attack is about. Okay, so we talked about these three different attacks, right? So these three different attacks basically are organized because the attackers have different goals. What kind of information they are trying to infer about the original data. So the most basic one is called membership inference attack. For this kind of attack, the goal of the attacker is the attacker has one record, for example, X star Y, and the goal of the attacker is to try to infer whether this record is in the training data set, meaning if it's a member of the training data. So that's why the name is membership inference. The attacker is trying to infer the membership of a particular target record. Right? So that's our membership inference attack. And again, the access model or the attack threat model here is that the attacker only has the API of the model, right? It does not know the internals of the model. It does not have access to the original data, right? All it trying to infer is the membership of the record. So stronger than that.
So
question.
Is this
yeah.
formally called an attack, or because it could, well, somebody could claim that somebody is doing it to see if their data is in the
Exactly. Yeah. The name we call it attack is because it's kind of reverse engineering, trying to figure out the original record, whether it's part of the original record. But later on, I'm going to show you, it's not just for attack, right? It's not associated with only attacks. It can be used for actually privacy auditing purposes. So you can use this to kind of evaluate the privacy guarantee of your model, to kind of evaluate whether your privacy enhanced technology like machine learning is properly done afterwards. So it is a kind of a tool that we can use for privacy enhancement purposes. So that's the membership inference attack. Now going further, you might ask or wonder, okay, what is the big deal of this, right? If I know whether this record belongs to the training data or not, because I already know the record, what is the privacy risk here? So it turns out this can be actually used as a foundation to do more powerful attacks. And some of these attacks include these attribute or data extraction attacks. So we're going to go back to that slide in a bit. So this data attribution or data extraction or attribute extraction attack, it means the attacker now is trying to infer the actual attribute or the actual data from the training records. And so it's just trying to extract X star, or maybe the attacker knows some partial records. For example, medical record. Maybe I know the name and I know the some address and some information about this record, but I don't know about the diagnosis. I don't know about other symptoms and so on of this record. Now I'm actually trying to use this model API to extract the extra attributes from the model about this record. Right? So that is the attribute extraction attack. And for generative models, I can try to actually extract exact data from the training data. So that's the data extraction. So these two types of attacks are called attribute extraction and data extraction, respectively. And the goal is to extract this particular attributes or the record from the data set. Question there? Okay. Yeah, question.
Yeah, there is a way that we can apply confidentiality, like on the data before training.
Yes, exactly. So that will be the next lecture. The second half of the lecture, we're going to talk about various techniques that we can actually use to try to mitigate these kind of memorization-based attacks. Yeah, great question. Other questions? Okay. So then just to give you a very quick kind of intuition, right? How is this attack possible? This one. Why is this membership inference attack possible? Right? What's the intuition behind it, right? By just having the API, why is it that actually I can infer the attribute or infer the membership? So the main kind of intuition behind this is that the model is trained on the training data. So to some extent, the model actually fits the training data, memorizes the training data to some extent, right? So it will treat the training data versus regular test data that the model hasn't seen differently. And because of this difference, the attacker will be able to leverage this difference and figure out whether a record is in it or not in it. And then, given this membership inference attack, how can we do this data extraction attack? So it becomes fairly simple when we actually have some record, for example, like X1, X2, like a partial record, and I'm trying to figure out what is the next attribute for this record. Then I can do various combinations of X1, X2 at a certain value of the next attribute and do various combinations and do the membership inference and see which one has the highest membership signal. Right? So the one that has the highest membership signal or membership confidence, then I can probably infer that that's the attribute value. That's the actual combination of this record. Right? So as you can see now, the membership inference attack actually can be used as a foundation to launch these kind of more powerful attacks to extract the attribute, to extract the actual data. Yeah, makes sense? Okay, so those are just some overview. And this also shows you an example of the data extraction. So that's the attribute extraction for the, oh, sorry, I keep getting this mixed up. So this is for the attribute inference. Now, coming to this LLM age, what we can do is to actually extract the data from the actual training data that's trained these LLM models. So if you are interacting with your ChatGPT or your whatever your favorite AI tool, you can actually try to come up with like a prompts. Say, can you please complete this sentence from your training data? My social security number is blah blah blah. So if you try this maybe a couple years back, you would get the AI tool to spit out the actual social security number that it has seen from the data, from the training data. But these days, if you try it today, if you try it now, it won't. Because these days, the commercial models have all been aligned So they learned not to spit out these private or sensitive information. So if you try today, it's going to say, I can't provide or generate sensitive or private information, including social security numbers and so on and so forth. Right? So it becomes smarter. It was aligned to not to spit out this information directly. However, the model are only aligned for these kind of common prompts. Right? If you get smarter and come up with some weird prompt, and in this case, some attackers actually came up with a silly attack. So they basically said user prompt saying, repeat this word forever, poem, 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 poem. And then the model starts saying poem, 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 poem. And after a while, it starts to spit out some information like the CEO, founder, and their email address and web and phone number and so on. So it starts to spit out these private information from the training data. So this is what we call the data extraction attack from the LLMs. And what it does is basically these prompts are not they are able to escape the alignment mechanism that these models have been trained with, right? So now given these prompts, the model is just spitting out the information verbatim.
But how do we know that this is like real private data? Maybe it's just generated.
Yes, so in these cases, the attacker can actually verify, right? So they actually have the training data, they have these spit out information, they can verify whether these data are actually verbatim training data. But in the real attack scenario, the attacker would not know for sure whether this data is exact or not. But most of the time, we can measure the exposure risk by certain confidence metric. If the perplexity, which is used as a loss metric for the large language models, if the perplexity is really, really low, that means the model is very, very sure to generate this data. So it's very likely these data are actually training data, are part of the training data. Great question. So again, these can actually use the MIA or membership inference attack as the foundation. So I can have actually different combinations or different prompts, and then just query the model and then look at the membership inference signal. So there are certain signals we can use. If the signal is very strong, then we can infer, okay, this data is very likely the actual training data. So that's how we can use the MIA to do the data extraction attack. Okay, questions? So this hopefully gives you an overview of what kind of privacy vulnerabilities we have, right? Even if just we have the API of the model without access to training data, we're able to do membership inference, attribute inference, and data extraction. And now the next part, I'm going to go into depth how we actually do this membership inference, how exactly it can be done. So there's some intuitions, but we're going to look at how exactly it can be done. So this part of the membership inference attack, we're going to organize it as first give you a quick overview. Why do we care about MIA? Why this MIA is possible? And how do we measure the effectiveness of the MIA, of the attack success? And then we're going to go into depths of several different kinds of methods, classifier-based and threshold-based. So we can think of the classifier-based as a supervised method, and the threshold-based is the unsupervised method, and MIA as hypothesis test is also an unsupervised method. And finally, we're going to look at how do we do MIA on the LLMs. So the first few methods are going to be focused on the general AI model, like classification model. And finally, we're looking at the MIA on the LLMs. Okay. So why do we care about MIA as asked, right? So there are several reasons. One is maybe there's some curiosity of the user of the model, right? We're just curious, what kind of training data are used to train this model? And is my actual record being used in this in training this model? So it's just curiosity of the users. And second, this model or this attack can be used as a building block for more powerful attacks, as we have seen, for data extraction and attribute extraction attack. And finally, this can be also used as a privacy tool for auditing the privacy risk of a model, or to audit whether or verify whether the machine unlearning has properly removed certain records from the model after the unlearning. So these are why we care about MIA, why we study MIA, not just for attack purposes, but really also for privacy enhancement, for understanding of the vulnerabilities. So why is MIA possible? Right? So as we mentioned very early on, very briefly, so here's some insight or kind of the reasoning or intuition behind why is this MIA possible. So normally we have some data and we use this to train a model. And then this model now is used as a prediction API to do predictions and so on. So it turns out this model is trained on this data, And these models always tend to fit this training data, right? And in some cases, maybe it's overfitted. So we are all very familiar with these kind of training graph, right? As we train over multiple epochs for the model, and the y-axis is our training loss versus the validation loss or test loss, right? So as we train over multiple epochs, our training loss usually is always decreasing, right? So that's because the model fits the data more and more, it learns more and more, so it makes less and less errors on the training data. However, on the other hand, if we look at this validation loss or test loss, first it might drop, right? Because it's kind of similar to the training data, but then at some point, the validation loss or test loss would go up. So that's the typical bias variance trade-off we have learned in the ML class, right, if you have. Right? So this is the point where the model starts overfit the training data, right? It starts to learn maybe the noises, outliers of the specific data points in the training data. Okay? So this is exactly the enemy or the reason that makes this membership inference attack or any of these inference attack possible, because now the model overfits data. So during the application or during the inference phase, if we give it some input from the training data and ask for the output, it gives us some classification probability output for different classes, right? So these are the logics we have. Now, if we give it another input that's not from the training data, we also get some classification output, right? Because the model has been overfitted to the training data, now these two classification output would look very different, right? Maybe this one, for the member, it will be very confident, right? One class has a very high probability, close to 100%. The other classes have low probability. While for this non-member, even if the non-member is classified correctly, but maybe the model is less confident, right? So the logics or the probability output would be more flat, right? So by looking at these two different classification output, then the attacker would be able to recognize, okay, maybe the top record is a member, the bottom record is not a member, right? So that's the main intuition behind this membership inference attack. Yes, Cyrus.
So the black box attack, they assume you have this classification attack.
In the bottom, yes, that's a great question. For the black box access, we do assume we have the output, which is the logit output, the probability associated with different classes. Yeah, not just a binary label.
That's the one layer before the output.
Not usually one. Yeah, the output layer. The output layer, yeah. But we do not know the internals of the model. Yeah. So we do know the output classification output, which is the probability associated with each class. Yeah, we do know this. Yes.
Does that mean the more the overfit the model is, the more the MIA attack is possible?
Exactly. That is great point. So we'll actually show you later on. It does correlate with the overfittedness of the model. So we can see if the gap between the training error and the test error. Oops, sorry. Yeah, if the gap is bigger, that means the model is more overfitted. The risk of MIA is actually higher. So that is a great observation, and it's being verified empirically too. Yeah. So actually, so that's later on. I'm gonna also show you. So these, for learning purposes, we want the model to generalize. We don't want the model to overfit. And from privacy aspect, we also don't want the model to overfit. So they actually they are aligned, the goals. Right? So if the model is overfitted, that means it's not generalizing well. It also means it has a higher MIA risk. So for all these purposes, when we train the model, we need to be aware that we don't want the model to overfit. Right? We can use a variety of techniques to avoid the overfitting risks. Okay, so that's the main intuition. And we're going to see later on how we take this intuition and build different attacks using different methods. Okay? So that's the intuition. Why is it possible? And now let's actually, before we go over the techniques, let's first look at how we can evaluate how successful this MIA is. Right? So now this MIA becomes a binary classification task, right? Given a target record, I want to figure out whether this record is a member or not a member. So it becomes a binary classification task. And the output can be just 1 or 0, member or not a member. Now, given this binary classification task, the way we usually do the evaluation is that we're going to have a bunch of records. Some of them are members, some of them are not members, and then we are going to do the attack and then evaluate how accurate my attack is. And to evaluate the accuracy, so there are several typical evaluation metrics we can use. For binary prediction or classification, their typical accuracy or precision and recall. And the accuracy is not very good because in this case, we are more concerned about whether we are actually able to classify a member, right? So the true positives are more important. So that's why the recommended metric is to do these ROC curve for the false positive and true positive. And also we want to do it log scale because we really care about the region of whether the model or whether the attack can do well in the low false positive rate, right? If I have a very high positive, true positive, but also I have a high false positive, then it's not very helpful, right? In the privacy case, always there's like this worst case privacy, meaning if I am able to figure out the membership of a few records very accurately, that means it's a very high privacy risk, right? So that's why these recommended metrics are either the ROC curve showing in a log scale and report the AUC, or we want to show the true positive rate given a very low false positive rate. So you can think of this as the region towards the left on the AUC curve. Okay, so those are the recommended metrics. If you ever looking at this MIA papers or tags, you want to look at these metrics. Okay, so that's a metric. Now, how do we do this attack? Okay, so we're going into details of some of these techniques. So the classifier-based MIA is the first seminal paper that introduces MIA attack. And then later on, there are several different methods that improves upon the classifier-based. And finally, there's MIA applied and extended on the LLMs. So we're going to first look at this seminal paper. This was published, I think, in 2020-ish, 2022-ish. Yeah. So it's called Membership Inference Attack Against Machine Learning Models. So recall this graph, right? We're just going to look at the difference between the classification output of a sample and try to differentiate them, whether it's a member or not a member. So the technique of this paper is that, okay, how about let's train a machine learning model or train a attack model to try to detect whether a record is a member or not. So this is what the technique of this paper is. It's going to train a model to try to recognize, okay, given this, whether this belongs to a training data or not training data. So now the question for you guys to think about is, how do we get the training data for this attack model? So think about this attack model. Now, for the attack model, the features would be the classification output and the class label. And the label or the output would be member or not a member, right? So that would be the feature and label for this attack model. So how do we get this training data for this attack model? We need to know these classification output. Given a record, we need to know this classification output, and then we need to know whether this record is a member or not member as a ground truth label to train our attack model, right? So how do we get this training data? Because we don't really know about this data that's used for training a model. We don't really know. So how do we get this training data to train our attack model? Yes?
Synthetic data?
Synthetic data, great, great. So we can maybe generate some synthetic data and then train some shadow models ourselves. And then we would know which record we used as training data or not training data, right? Because for the target model, we don't have access to training data, so we can't use this. We don't really have the ground truth. But if we have some synthetic data or data on our own, we train our own model to kind of mimic the behavior of the target model we're trying to attack, then we know the ground truth, whether each record is used as a member or not a member, right? So that is the main idea behind training these attack models.
What if it mixed up with other data as well? Then it's not so easy, right? I guess. I mean, training on your own data might generate completely different answers than having it trained with, if your data appears within, a big collection of other documents.
Yes, exactly. So this actually becomes a challenge. How do we get the synthetic data or whatever data that kind of mimics the data, right? We want the data to mimic this data. So we'll get to actually in a little bit how we can generate data that mimics this data without seeing the data. Okay, so great ideas. So let's see how this attack actually works, right? So first, we're going to do some shadow model training. And the goal of this shadow model is really just to mimic the behavior of the target model, because we don't have the target model internals, and we don't have the data that's used to train the target model. So we're going to train some shadow model that mimics this target model. And in this case, so we have some, let's say we have some synthetic data, we generated some synthetic data, and then we use this synthetic data to train our shadow model. So this is the target model we don't have access to, right? So we're going to generate some shadow training data and train our shadow model. So we have a bunch of shadow models. Now for each of this shadow model, then we have the members, right? These data that are used to train this shadow model, we know they're members, right? And then we can generate some other similar records that are not used to train this shadow model. Those become non-members, right? So now we have the members and non-members as our ground truth data to train our attack model. So that leads to our step 2. Okay, so, oops, sorry. Yeah, that leads to our step 2. Here, we would have some shadow training data that's used to train the shadow model. Now, these data are going to be associated with the in label, which means they are member. And then we have some other test data set that's not used to train the shadow model. Now, these data are going to be associated with a out label, which means they're non-members. So now we can actually use these to train our attack model, right? So our attack model now has the feature, which are the probability output of the shadow model output, and then the labels in and out, and then we can use them to train our attack model, right? Once our attack model is trained, then given a record, we can give it to the target model, and then given the output of the model, given the prediction output and classification level, we give it to the attack model. The attack model is going to give us whether it's an in or out, right? So that's the whole process of the attack model. Yes?
Okay, the training data are the synthetic data that we got, but how do we get the test data? We just divide them?
Yeah, exactly. So we can generate a bunch of synthetic data, use a part of them to train our shadow model, use the other part as our test data or non-member data. Yeah.
And this model is basically trained to differentiate between them.
Yes, exactly, yeah. The whole purpose of the attack model is to differentiate a member versus non-member, right? Based on their output from the model. Yeah. So now the only remaining question is, how do we generate the synthetic data that are similar to the original training data? Right? So there are 2 ways. The first is, if we do have some prior knowledge on the data distribution that's used to train the data, then we can just maybe sample some data from a public domain. But what if we don't have this distribution, or we don't know about anything about the data that's used to train the model? So one way we can do is to do some kind of a model inversion attack, trying to reconstruct the data themselves. The way we can do it is that we can start with a random sample and then query the target model with the random sample multiple times, right? And then based on the model output, based on the model confidence, I can slightly change my features of the sample in order to get a high confidence output, right? So the idea is, again, similar insight, similar idea behind the membership inference attack, right? If the record is a training record, the confidence will be high. The probability output will be high. So I'm just going to gradually modify my record until I get back a record that gives me a high confidence output. Then I can kind of infer that might be a training record. Question?
So why do you assume that you have privilege to query the target model?
So that's the kind of basic assumption, right? The setting. So the model has an API. So I'm just going to use the model API to do, let's say, query a sample and get the prediction output and so on. So a lot of times there's like ML as service, right? So the model API is published. Or even in a hospital setting, I work with hospitals, so they have models and physicians have access to model API. So they can give it a record, like a patient record and so on, and get back the prediction output. How high is the risk of this patient in terms of sepsis and so on. So
you are doing like the queries multiple times, right?
Yes, you can do it multiple times. So so there are certain, for example, we can actually quantify this as a budget, like attack budget, right? So if you can only query the API limited number of times, then you may need to be careful in terms of how to design your attack. But in general, for these kind of attacks, for example, in this particular case, we do need multiple access to the API in order to generate the synthetic record. Yeah, so that's a great point. So these are all kind of related to the adversarial power. The more access, the more number of queries you can query, the higher the power, the adversarial power, and maybe the stronger attack you can do. Yeah. Great questions. Other questions? Okay, so that's the machine learning based attack. And this is the first time that was introduced. So it reported some results. In general, for these kind of synthetic data, using shadow model trained on the synthetic data, the paper was able to report 89 overall accuracy for the attack. But then, of course, this was criticized by later works that by simply reporting the accuracy is not very good, because this just means the model may be very good at predicting whether a member is a non-member or whether a record is a non-member, but it's not very good at predicting whether a record is a member, even though overall accuracy is good, but it's just because these non-members have a very high loss or very low confidence. It's very easy to tell if this record is not a member, but it's not very good at detecting whether a record is a member. So that's the reported results of this paper, and later on, it got improved by several other works. Okay. So this actually shows the insight that's already brought up by you in terms of the overfitting versus the MIA risk. So this actually exactly shows that. So these are different data sets they tried, and then these are the training accuracy, and this is the testing accuracy, and then this is the attack precision, right? So you can actually see the difference between the training accuracy and test accuracy. The higher the difference, it means the model overfits the data more, right? So you can see towards the bottom, the difference is very high between the training accuracy and test accuracy. That means the model has a very high overfitting level. And you can also see the attack precision actually increases as the difference between the two increases. Right? So that kind of verified the observation that you already mentioned, that the more the model overfits the data, the higher the attack risk, the MIA risk, membership inference attack. Right? So again, this kind of verified this insight that the paper also raised. So from one hand, we have this training set, which is a subset of samples from this whole data universe, right? We're using this training set to train our model. And from a privacy point of view, we care about, does the model reveal or leak information about this particular training data set? From a learning point of view, we care about whether the model generalized the data outside the training set, right? We want the model not only work well for the training set, we also want the model to work well for the test data set that the model hasn't seen before. So again, actually, if we look at these two things, they actually share the same goals, right? We don't want the model to overfit this training data so that it increases the MIA risk or data leakage risk. We also don't want the model to overfit the training data so that we want the model to generalize well for the other data. So from both privacy and learning point of view, these two goals are actually aligned. So that's the nice thing about understanding the reason behind this privacy attack, and also shed some light when we are trying to build these solutions. We want the model to generalize and decrease the privacy risk, the memorization specific risk. Okay. So this just shows the privacy and utility, they are actually aligned. So it's not a lost cause that we want to build privacy enhanced machine learning solutions, right? They're not in direct conflict. Well, most of the time they are kind of common wisdom or common understanding. If we want to build privacy enhanced solutions, we sacrifice utility, which is true in most cases in some extent, because the privacy techniques we use are usually, for example, introducing some noise to the model and so on. So it does have a privacy utility trade-off. But fundamentally, if we're thinking about these two aspects, they are actually aligned. So it's a matter of how do we design these kind of techniques to improve both the privacy protection and utility or generalization capability of the model. Okay, questions? Okay. All right, so that covers the classifier-based MIA, one of the early, or actually the most earliest work that introduces MIA attack. And then we're gonna look at some separate or alternative methods to do this MIA. So the kind of what we have seen so far, the classifier-based MIA, as we have seen, it does not work as well, actually. And also, there are some disadvantage or limitations. It's because we need to train all these shadow models and train our attack model. Right? And the attack model, performance of the attack model really depends on how strong these shadow models are. If the shadow model, if the synthetic data we generate are really, really good, and then our shadow model are really, really good in terms of mimicking the target model, then maybe the attack would work well. But otherwise, it may not work very well. So that's the kind of drawback of the supervised approach, right? We need the data, we need the label to train our attack model. Now, after the MIA was introduced, people started looking at, okay, can we do this in an unsupervised way? Meaning without training a model, just looking at the loss, can we try to figure out whether a record is a member or not? Right? So this is the basic paradigm of this threshold-based MIA. It's actually much simpler than the ML-based MIA or the classification-based MIA. So what we are going to do is, given a sample or a target record, we're going to give it to the target model, and then we're going to get back some score. So we're going to look into the details of what these scores are. So we're going to look, get back some score, and then we can simply apply a threshold, whether this score is smaller than a certain threshold. If it's smaller than a certain threshold, maybe it's a member. Otherwise, it's not a member. So that's just a simple threshold-based technique or method that we're going to use to try to detect whether a record is a member or not. So what would be a simple score here? Can you come up with a simple score that can be used to detect whether a record is a member or not? What would be the simplest score we can use? Or what would be the simplest signal here that we can use?
Confidence.
The confidence, exactly, the loss, right? So the main intuition is that given a training record or given a sample, the confidence will be high, the loss will be low, right? So we can just use that. If the loss is smaller than a certain threshold, or if the confidence is greater than a certain threshold, it will be a member. Yeah? Otherwise, it's not a member. So that's exactly the first work. It's a simple loss-based attack, right? It's just going to, very simple as we mentioned. So we're just going to give the X to the F and then get back the loss, and then see if the loss is smaller than a certain threshold gamma. If it's yes, then it's a member. Otherwise, it's not a member. So the reason this works is that we can actually see the kind of loss distribution of members and non-members. So in this graph, the x-axis is the cross-entropy loss for the typical classification task, and y-axis is the fraction or probability of the samples belonging or having certain cross-entropy loss, have certain loss values. So you can see the blue one is the members, right? And the red one is the non-members. So in general, this is very intuitive because the non-members have higher loss, right? The model is less confident. And the members in general have a lower loss. Yeah? So that's why we can use this loss to differentiate these two members versus non-members. Yes, Sarah?
Is this the loss function of the target model?
Yes, the loss output,
Access to-
the loss output of the target model. So the loss is just cross-entropy loss, right? So you have, for example, given a record, you know the ground truth, and then you have the
So you
probability.
assume the cross-entropy loss and just find the difference between the two distributions, the classifications.
Yes, so this just kind of illustrate if I have a bunch of samples, I know these are the members, these are the non-members. If I plot them, it's going to look like this, right? But in the real-time attack, all I know is just one loss, right? So I need a threshold. So maybe in this case, I put a threshold here, right? So this would be my threshold. So given the record, I have the loss. And then if the loss is smaller than the threshold, I say it's a member. Otherwise, it's a non-member. But as you can see here, this would not get us 100% or even good accuracy, right? Because these two actually overlaps, right? Yes, questions? Yes, so it is specific to data sets, specific to models, specific to everything. So that is the question here too. This attack is very intuitive, very simple, but it would not work very well, right? Because this threshold is very hard to set, right? It's a very specific data set, very specific to the model, also very specific to different samples. Different samples may have different hardness, right? So you can imagine here, right? So for these samples, these are the non-members. It's very easy to differentiate them. However, for this part, the red part that overlaps with the blue part, these part of samples, we call these samples maybe easy samples, right? Or inliers, meaning they're easy to classify. They are, even though the model hasn't seen them, they can still classify them correctly. So they're kind of like inliers, meaning they're similar to the data we have seen in the training data, right? So these part of samples, even though they're non-member, their loss is very small. So in this case, we can't really differentiate these, right, from the members. So that is the limitation of this loss-based attack, as you can see, right? It will be very good at classifying these non-members that have high losses, but it will not be very good at differentiating these members versus this inlier or easy non-members. Yeah, makes sense? Okay, so we need a way to actually calibrate our loss here, maybe to have a better signal, like a calibrated signal to tell us better, to help us differentiate these two better. Yeah. So there are a couple of ideas that came up in the literature, how we can actually improve this kind of loss signal. So one idea is we want to make sure to differentiate the members versus non-members, and the members are kind of fitted by the model. So the model actually memorizes the specific information about this member. But for these non-members, they can be easily classified by this model, not because the model fit these samples, not because the model memorizes the samples. It's simply because these members are easy. Right? So one way we can actually take into this account is we can train a reference model, like a shadow model. So we keep using this shadow model idea, right? So we can actually train a reference model that using similar data, similar distribution. And if these records also have a low loss in those reference model, that means these members or these records are just easy members, that easy records, easy records that can be easily classified by this model. It's not because they are memorized by the model. So there are two cases that we need to differentiate, right? Whether this record is memorized by the model or whether this record is just an easy member that can be easily classified by any kind of model or similar models. Right? So that's the idea behind a reference model-based attack, where we simply train a reference model using some similar data distribution, and then we get the loss from this reference model, and then we calibrate this loss by this reference model loss, and then we take the difference and then compare it with a threshold. So that's the main idea behind the reference model-based attack. So we take the loss from this model, and then we take the loss from a reference model. So this should be a reference model, theta reference. So it's just a similar model. So now the idea or intuition behind this is that if the record is memorized by this particular model, it should be performing very poorly by the reference model, right? So that means that if the difference is high, that means this record is very likely a member. But on the other hand, if the record also has low loss here, but on the reference model, the record also have low loss, then that means the record is just a very easy sample. So the difference is small, so it's not a member, right? So the main idea behind this is to try to differentiate, these part, right? Just differentiate this red samples and this blue samples. So by doing this, turns out now we can actually well separate these two kinds of samples. So this is just by using the loss. This is the training data. This is non-training or the non-member sample. We can see they're kind of overlapping. But then if we use the reference model-based calibration, take the difference between the two losses, now these members and non-members are well separated, or much better separated. So if we now use this as a threshold, we can make most of the differentiation correct, right? So we can differentiate these two type of samples. Yeah.
Why do we assume here that the shadow model will be good in the easy records? Is that?
Yeah, so that's a great question. So you always pick the kind of the major limitation of this work, right? So this reference model-based attack very much depend on the reference model. So if the reference model does not perform well, as I'll show you actually in a little bit, then this attack does not work very well. Yeah. So to kind of mitigate this kind of limitation, then people came up with another simple idea. So the idea is instead of using a reference model that relies on additional extra data and additional shadow model and so on. So what if I just rely on the sample's neighbors? Yeah. So the intuition is that if I am a sample, if I am a member, then if I take a look at my neighbor samples, and my neighbor samples, they're not members. So if the difference between my loss and my neighbor's loss are high, that means very likely I am a member. On the other hand, if I am very similar to my neighbors, that means I'm probably not a member because the model hasn't seen all of us. Does that make sense? So that is the neighborhood-based calibration here. So taking a X, I'm going to generate a bunch of neighbors, xi tilde. So these can be generated by different ways, like a Gaussian noise-based perturbation, or if it's image, I can do different kinds of image processing, like rotation and so on. Get a set of neighbor records, and then I take their loss, and then I take the average of their loss, right? So this becomes the mean loss of my neighbors. And then I take a difference between my loss and my neighborhood loss, and then this difference now serves as a signal for doing a membership inference attack, right? So the higher the loss, or the higher the difference, that means actually the smaller the difference, the more likely it's a member. Okay, so what is so the if I'm very similar to my neighbors, so that means I am not going to be a member. So I think here it might be a little bit flipped. So yeah.
If I am similar, the average will be small.
Yes.
The average will be small, the difference will be high.
If my neighbors are also very confident, right, and then I'm also confident, though the difference is small, so in that case I should not be a member, right? So the difference, if the difference is high, it means a member. Yeah. So this needs to be flipped. But basically the idea is I look at me and then I calibrate my loss based on the neighbors. So the reasoning behind this is that if the model has seen me, then it should somewhat treat me as differently as my neighbors. Otherwise, it should treat me the same as my neighbors. Right? So that's the intuition. So here it shows this illustration. So basically, for example, given a text, I can actually generate different neighbors and then query the target model and then take the mean. And looking at this threshold, if it's low, I do a member, otherwise I become a non-member.
What can we mean by neighbors? The samples that the model have seen this training samples before, right? So the neighbors that are behind this sample, not after.
That's a good question, but from attacker point of view, I don't really know, right? What neighbors the model has seen, what neighbors the neighbor has not seen. So all I can do is just generate a bunch of neighbors around me and then use their loss, average loss, as my kind of a reference to see. Yeah. Yeah. So this kind of just circumvents the need to train a separate reference model. Now I just use my neighbors as a calibration, right? So these are the two different ways to do the calibration for the loss in order to get a stronger attack signal. So here we actually shows the comparison between this reference model-based MIA and the neighborhood-based MIA. So here the two lines are the neighborhood-based, and then the dots are the reference-based. So we have different dots. It's because we may have different reference models. So these x-axis shows the validation PPL, the perplexity or loss of the reference model. So you can see if the reference model are very weak, then that means our attack is actually very weak. So the y-axis shows the true positive rate at a very low false positive rate, which is a metric for evaluating how strong our MIA attack is. The higher, the stronger the attack. So you can see the reference model plays a big role in terms of attack performance, right? So the reference model, if it's weak, the attack is very weak. And if we are able to train very strong reference models, then our attack can be very strong. But on the other hand, the neighborhood-based is just a constant. So that shows the two. So these are the two kind of state-of-the-art membership inference attack. So when we talk about inference attack, these two are commonly used, very easy to use compared to the machine learning or classification base because we don't need to train, right? So we can simply take the loss and do the reference or do the neighborhood and then do the attack based on threshold. So this is the two reference-based or loss-based attack. So that kind of concludes the threshold-based MIA. And then later on, there's one more attack that is considered as the strongest attack, which I'm going to tell you, the MIA as a hypothesis test. So this is by far the strongest MIA attack that people have known so far. So if we were to use like a benchmark MIA, we can use both the threshold-based MIA and MIA as hypothesis test as an evaluation tool. So how does this membership inference attack as hypothesis test work? So this is a paper that was pretty recent, called Membership Inference Attack from First Principles. So the main idea behind this is to look at how does membership really mean. So it means, if we train a bunch of models, if we use a bunch of models that has this record, and then if we have a bunch of models that does not have the record, then that's going to tell us whether the model would look like, how the model would look like, given the record is a sample, or given the record is not a member, or given the record is a member. So to differentiate this, the paper basically is going to do training of two worlds. So one is to train a bunch of shadow models with the X. One is train a bunch of models without the X. Okay. So then what it did is it actually illustrated how these two worlds are actually different for different kinds of samples.
X
So-
is one record?
X is one record, exactly. So this attack is going to be very expensive. So that's why it's like a very theoretical attack, but you can actually do it in practice, but it's going to be very, very expensive. So given X, for example, it may be a member or not member, just given one X, I'm going to train a bunch of models. First bunch of models is trained with this X plus a bunch of other records, right? And then another bunch of models is trained without this X, but with some other records. So you can think of this as in models and out models. Right? So it's slightly different from what we have seen earlier, where the shadow models are used differently. Here, a bunch of shadow models are trained with the X, a bunch of shadow models are trained without X. So then they actually illustrated the differences between these two member models and non-member models. So here, for a record that is easy to fit, and an inlier, meaning it's very simple, similar to a record in the training data, you can see these two worlds are actually overlapping with each other. Given that sample, if the model is trained with a sample, if the model is not trained with a sample, the loss of the sample is actually the same. So this is plotting the loss from these member models and non-member models. Does that make sense? So if you look at this, it's also given run record. So this is a bunch of models that are trained with the record. And this is a bunch of models that are trained without the record. And then we plot the loss from this model. So you can see in this case, if a sample is very easy to fit, but the sample is very different from the training data, we can see these two bunch of models are very different. Does that make sense? So the in model has, in general, very low loss, and then the out model, in general, has a very high loss. So in this case, in this particular case, it's very easy to differentiate these two worlds, right? To differentiate whether X is actually used in the model or not in the model. So the main idea behind this work is to look at these and say, we need to look at the samples and look at their per sample difficulties or per sample hardness. All the previous work, right, we have seen, if we look at this threshold based, we are actually looking at this as a single threshold. So we're not looking at per sample difficulties. And those reference-based model calibration or neighborhood-based calibration actually takes into account the per sample hardness to some extent, but not directly. So this work actually takes this per sample hardness directly into consideration. So the way it does is that the intuition is given any record, I'm going to train a bunch of models that has this record and a bunch of models that does not have the record. And then given my target model, I'm going to see whether the target model belongs to this distribution or this distribution. If the target model is more similar or belongs to this distribution using a hypothesis test, then I'm going to say this record is a non-member, is a member. Yeah, does that make sense? So that is the main idea behind this. I'm going to train a bunch of models, get the distribution, and then given the target model, I'll see if the target model is more similar to this distribution, belongs to this distribution from a hypothesis test, or belongs to this distribution. If it belongs to distribution, it's a member, otherwise it's a non-member. So that's the main idea behind this work. So this is the details. We're going to train a bunch of shadow models with X and a bunch of shadow models without X. And then in order to do the hypothesis test, we're going to simplify it. Just take the loss of the model output and then approximating them using Gaussian distribution. So I'm going to approximate this with Gaussian distribution. And then after I do that, I only need to record this distribution using the mean and variance. So based on the mean and variance, I can perform a hypothesis test. Given a target model, I can see whether the target model belongs to either of these distributions. So that's what the hypothesis test is doing. So this is the details of the attack, basically as what we have seen, or what we have said earlier. So as you can see, this.
So assuming the loss is Gaussian distribution is the right assumption.
Yeah, it's not necessarily the right assumption, but they have some technique to actually help with that. So if we just look at these, you can see these are not really Gaussian assumption in this case. These are not following the Gaussian distribution. So what they did is actually they did some scaling here. Once they have the confidence scores, they actually scale it so that it's more similar or follows the normal distribution, Gaussian distribution a little more. So that's the little trick they did here to make it more Gaussian distribution-like. So that's a great point too. So that's the little step they did there in order to exactly address that question. Yeah. Okay. Okay, so yeah, so that's the technique here. As you can see, it's very first principle based because it almost like a brute force. I train a bunch of models with the X, without the X, and then see where my model belongs to, right? So it is very expensive. However, it is very strong. It is the strongest attack so far. If we talk about MIA, people would talk about Lyra attack as the strongest attack. And here you can see the hours, or what they meant hours is the Lyra attack. And then these are all the previous attacks. Some of these we have already seen, like reference model based, loss based, neighborhood based, and some of these ML based. So basically, when we show the true positive rate at a very low false positive range, this Lyra attack has the strongest true positive rate. It's the strongest attack. Okay, so that was the kind of conclusion of this attack. So now I actually shared with you all the kind of representative and state-of-art MIA attacks and also the metrics. So if you ever want to perform an MIA attack, the recommendation would be try the loss-based, reference model-based, and neighborhood-based, and the Lyra-based. The Lyra-based will be the most expensive, but would be the most powerful, the strongest attack. Okay, now let's see how we can actually apply this MIA on the LLMs, right? So given the LLM model, how can we actually figure out whether a sentence that looks like this, for example, whether it belongs to the training record or not? So that was the application of the MIA on the LLMs. So the way we train the LLM is usually use the causal language modeling, right? So we're given a bunch of like words, prefix words. We want to predict the next word or next token. So that's the how usually the LLM is pre-trained using this causal language modeling task. So now given this, we can actually use this probability output or perplexity output as our MIA signal, right? So a direct application of our MIA that we have seen so far, directly applying it to the LLM is that we can give the record, the sentence, and then given the prefix and use the GPT-3, for example, to predict the next token. And then we get the next token probability output, like a confidence vector. And then we can do this iteratively, like auto-regressively, right? Just given the prefix, predict the next token, give the a few more words and predict the next token, and so on and so forth. So for each token in this sentence, we will get a probability vector. And then we can actually aggregate them into an average probability vector, and then use that as our loss signal, right? The lower the loss, the lower the perplexity in this case, the higher likelihood it is a member. So that would be a straightforward application of the MIA we have learned to the LLMs. Now, using a threshold, exactly, yeah. And you can also use a reference model based and so on, right? So given a threshold. So the main difference is that here, instead of one classification output, here is an autoregressive token prediction, right? So given one token, we predict next token, given two token, we predict next token, and so on and so forth. For each token, we get a probability vector, and then we can aggregate them and use that as our overall loss signal, and then compare that loss with some threshold and see whether it's a member or not, right? So that's the direct application of the MIA on our LLMs using loss. Instead of loss, now we're using perplexity or aggregated perplexity for all the tokens. Yeah. So that was the basic application. Now this work is the most representative work on MIA on LLMs. It actually improves the basic attack using a very simple technique. So the main intuition behind this is that if we aggregate the probability vector of all these tokens, so some of these tokens may not mean that much because some of these tokens are not very specific to the sentence, right? Like was or at. Some of these generic or general tokens does not carry as much information. So the main idea behind this work is that we're only going to look at some of these important tokens. And what do we mean by important tokens? If we look at these tokens, if some of the token has a very, very low loss, that means this token is very specific to this sentence or very specific or very strongly correlated to the previous tokens. So we're only going to take the minimum K percentage of the tokens that have the small probabilities, and then just aggregate their loss or log perplexity, and then use that as our attack signal or MIA signal. So that is the main idea behind this min K attack. Right? The only trick it does is just to take the minimum K percentage of the tokens that carries the strongest signal of the sentence, and then use that as attack signal. And turns out this small trick, as simple as this, actually outperforms the other technique, the basic technique as we have seen. If we look at all tokens versus if we only look at the min K tokens, and then if we also compare it with the neighborhood-based calibration, right? So this red line is the min K probability. So it outperforms this neighborhood-based, and the basic PPL is the loss-based. Right? So it does not compare, it did not compare with the reference model-based. It compared with the neighborhood-based and the direct loss-based. So it turns out it outperforms the baselines, just doing the simple trick. So that kind of gives us some insight, which we will actually go back to later on for the privacy enhancement techniques, that these tokens actually carry different importance, right? Given the sentence, these tokens have very different contribution to the sentence. So later on, we're going to actually come back to this point when we are trying to build privacy enhancement techniques. We're going to also take advantage of these insights. Different tokens may contribute differently to a sentence. Just keep that in mind in the back of your mind. Okay. So then this is the technique. As you can see, it's very simple, but the main contribution, one of the main contributions of this paper, this work, they also introduced a benchmark data set, because for membership inference attack on these pre-trained, like GPT-3 models, it's very hard to know whether a sample is a member or not, right? We don't really have access to the data that's used to train these GPT-3 commercial models. So the paper actually introduced a benchmark data set that's kind of smart, clever in a way that it uses a time cutoff to simulate the member data versus non-member data. So it takes all the Wikipedia data set and takes all the events after 2023 and treat these as non-member data, and then take all the events or data before 2017 and treat these as member data. The assumption is that all the commercial models that are released after like 2020-ish, they actually used all the data from Wikipedia before 2017 as their training data. So basically anything happened after the release of the model, we can treat them as non-member data. So that's the kind of a one smart way to simulate, to know the ground truth, whether this data is actually training data or not. So they can evaluate their MIA technique on these pre-trained GPT-3 models. Okay, so that's kind of one of the main contribution of this work. And then people actually use this data set to evaluate MIA on the pre-trained models. So here are a few case studies. What is MIA is used for LLMs in particular. So one technique or one use case could be to differentiate or to detect whether the pre-trained model or the GPT models or these large language models use copyrighted information. So not just for privacy reasons, right? Here it might be copyrighted content. We want to detect whether the model is actually using copyrighted content. So for example, this work did different books and try to do the MIA using this book information, like sentences from the books. And turns out a lot of these books are actually used, copyrighted books are actually used in these pre-trained models. So this is one use case to detect whether copyrighted.
Are there any regulation that really depends on such MIA attack, and you can like sue some people like OpenAI or
Yeah, exactly. I mean, there are some New York Times articles on that, right? But again, but these are not, because you can't for sure verify it, right? These are just research results, evaluation results. You don't.
Also, on this point, I wanted to ask earlier, because of the New York Post, you know, and New York Times basically sued, right, OpenAI.
Yeah.
So, and you mentioned earlier that even, you know, a minor, you know, a response is an important thing, and that's the case, right? So even if a single, let's say, paragraph or a page comes up, that's already enough to verify that maybe there is more to that.
Yeah.
So is there, do any of these like research results also make their way into, you know, legal cases, or we don't know that?
Not that I know of, besides that New York Times article, but I think all of these are going to raise more awareness, and eventually I think it will make it to the legal argument and maybe hopefully lead to more regulations and so on. Yeah. And also depending on these companies, some companies are more reliable, more responsible, and then these other companies, maybe they just get whatever hold of data they can and train their models.
Because OpenAI takes full responsibility, right? They say like legal responsibility for the output they give, which is unclear how it works. But
yeah, and also you don't really know what they are doing. They may actually do some post-processing filtering and alignment and all that to kind of hide the fact they use these data, right? So that they don't exactly regurgitate or generate these contents. So there are a lot of things happening behind the scenes that we don't really know. So these are kind of reverse engineering, but then you can argue, I guess for legal cases, these are probably not enough of evidence. So, but then I think again, these are all raising like awareness and hopefully leading to the right direction of building more responsible large language models. Yep. So this for copyright content detection. And then another use case is to detect whether there's a downstream task contamination, right? A lot of times these days, I'm sure many of you do, use the LLMs to do your task, maybe use the LLMs to do like a zero-shot learning or few-shot learning for your own tasks, right? And sometimes you get surprisingly good results. And maybe that could be a flag for you if it gets like a really good result. It may be because whatever task data you have, the model has seen it already. The language models has seen already the data you're trying to predict or whatever, right? Because you don't really know. So that's what we call the downstream task contamination, right? Your data has already been trained by using by these pre-trained models. So how do we actually detect these cases? Yes.
Those are benchmarks for LLM. So when they define the benchmark, they should take into consideration that it's not in the training data.
Well, they don't publish exactly what data they use for their training data, right? Especially these structured records, they probably get hold of a lot of these structured data records that we don't really know. I mean, obviously all these machine learning, probably like these IC machine learning repositories, all these data sets, they're probably used. But then even for these some other data, we don't really know. So that's why I think there might be a flag there. sometimes you get amazing results. You may be cautious. You should be cautious that maybe the task is already contaminated, right?
So how to evaluate the benchmark? For example, this is in the Q and so on, and tools for QA are in Llama papers. So what else to do then to evaluate the language model? Because this is the benchmark that we have. Should we design a benchmark or?
Yeah, so here it gives us some technique to do the kind of detection. So what they did is that given some of the data sets, they actually, given the pre-trained model, they fine-tune the model using the, for example, downstream data sets. And then they did the MIA attack on these fine-tuned model. And then here are the results they can see, right? These are the data sets. So they can see using these different MIA attacks, these are the AUC score. Right? So if you see, for example, if the model is trained by the IMDb, the AUC score for the MIA is very, very high. So what you can do as a potential way, right, is that given your benchmark data set, you can actually launch MIA using this benchmark data set and see the AUC score of the attack, right? If the attack is very, very like almost 100%, that's for sure. That's, I mean, very likely that model or the pre-trained model already seen this data. Yeah. So these are just some basic techniques or tools you can use as a use case of this MIA, kind of trying to detect whether your task data has already been contaminated by the model. Yeah. And also this MIA can be used to audit machine unlearning. So we're going to actually introduce this machine unlearning as a privacy enhancing technology in the second half of the lecture. Basically, the idea is given a pre-trained model. So now if we realize, oh, this Harry Potter book, the copyrighted book has been used by this GP2, T2 models or any of these models, we want to unlearn this set of content. So we can perform machine unlearning to update the model so that the model forgets this knowledge. So we're going to introduce this unlearning technique later on. But then after we do the unlearning, we want to do some auditing or verification to see whether the model indeed has forgotten about this data, right? Has get rid of this data. So we can perform this MIA to actually audit the unlearning. Like given, for example, a sentence from the Harry Potter, we can see whether the membership inference attack gives us a very high AUC or very high signal. If it's still very high, that means the record has not been completely forgotten. So the model has not been erasing the record successfully. So this is the use case where we can use the membership inference to audit the unlearning purposes. Okay. All right, so that's the use cases. So now let's briefly discuss or kind of summarize what are the open challenges. So it turns out when we do the MIA on the LLMs, as you can see earlier, even though the result actually is fairly good, is reasonably good, but then later on, there's more large-scale evaluation of MIA on LLMs, and turns out it's actually not easy to do MIA on LLMs. The main reason the previous work I showed you actually showed good results is because of the evaluation data set, right? Because of this knowledge cutoff, anything after 2017 or 2023 is considered as non-member. So there's actually temporal shift. So the non-member actually are very different from the members in the training data set. So that's why it actually shows pretty strong success rate for the MIA. But in reality, if both members and non-members belonging to the same period, belonging to the same distribution, it becomes very hard to differentiate between members and non-members. And the reason contributing to this are mainly twofold. One is mainly because of the characteristics of the LLMs. One is the LLMs use a large, like vast amount of data to train a model, which makes it very actually generalizable. So that goes back to our point, the generalization versus the privacy leakage risk, right? So the large language models actually has a very strong generalization capability. So it makes it actually hard for the MIA attack. So it means the MIA risk is actually fairly low. And the second is that most of these standard like LLMs, large LLMs are actually pre-trained only using one epoch. And this makes it, again, very generalizable because we know that training more epochs is going to overfit the data, right? By early stopping really just one epoch training, it's actually very generalizable. It does not overfit the data. So both of these two reasons makes the MIA actually very hard on LLMs. And another reason is that it's text-based. So when we're talking about a sentence, whether it's a member or non-member, so there are some members versus non-members, and the overlap between the members and non-members can be very high, right? If you have like a sentence that belongs to the training data set, if I have some partially overlapping sentence, it's hard to say whether it's a member or not a member. So because of this ambiguity between the differences between the text sentences, it's going to be very hard to differentiate these member versus non-member. And also another point that's worth mentioning is that how realistic or how useful this MIA is, right, in terms of LLMs. For classification models, it makes sense. We want to figure out whether a record or whether an image belongs to the training data set. But for the LLMs, large language models, does it actually help us to figure out whether an exact sentence is part of the training record or not? Maybe it helps, but maybe also worth thinking about additional attacks that are more aligned with the privacy leakage, right? Maybe, for example, we'll care about the user level leakage, not the sentence level leakage, right? Or we care about the PIIs, protected information, like address or some of these sensitive entities. So we can probably design attacks that are more aligned with these kind of privacy leakages that are more of the interest to actually users, right? So these are a lot of open challenges in terms of doing this MIA on LLMs.
So can MIA also be used for the task of plagiarism? Because it's also a type of membership, but it's on the opposite side of things. So basically, you want to see whether, certain type of output belongs to a certain model, let's say.
You mean
Can this
plagiarism?
MIA, well, yeah, because currently these rely mainly on so-called watermarking.
Yes.
So they presumably some of these models watermark their results, so somebody can recognize whether a certain output has been produced by a model.
Right.
But it's unclear, whether the results we get from the LLMs are watermarked, and whether or not there is any plausible way to identify this membership, like the plagiarism cases,
Right.
like whether or not some output came out of a model.
Yeah.
So-
So I think, yeah, in a way, I think it can help.
It can help.
Yeah, it can help.
But it
yeah.
has not been investigated.
So in terms of detecting plagiarism, yeah, not that I know of. Yeah. But I think it could be an interesting, direction. Yeah. Okay. So we have 4 minutes left. My original plan was to tell you a little bit about our recent work, a backdoor MIA, that we improved upon MIA to actually make it even stronger, given this pre-training and fine-tuning paradigm. So I can probably do this in 3 minutes. So the main idea is that right now, we're only looking at the tech interface where we have the model API. Right? But increasingly these days, we have this pre-trained model, right? We download from Hugging Face, we download from whatever GitHub, we have this pre-trained model, and then we fine-tune our pre-trained model using our private data. And then we release the model API. So now this actually gives some additional attack surface, right? In addition to the model API access, now we're actually releasing the pre-trained model. So if the attacker gets hold of the pre-trained model interface, it can actually perform an even stronger attack. So the main idea behind this work was that can we manipulate the pre-trained model to amplify the privacy risk of the fine-tuning data by using the model API? So the intuition is actually very simple. Again, we're looking at this training phases of a model. Right? So it turns out there are actually several stages of training a model. And when we train a model, in a very early stage, the model is trying to fit and memorize the data points. So this is the utility, the validation PPL, right? If we move from right to the left-hand side. If we go this hand side, when we train more epochs, these are different checkpoints of the models. So the validation PPL becomes smaller, the utility becomes better. And then at some point, the model actually moves into a memorization only stage. If we keep training, at this point, the model utility does not improve. However, the memorization risk actually increases. This is when the model becomes memorizing the sample specific information. They stop learning about the patterns, the general patterns. And at some point, if we continue training, it goes into the overfitting stage. that's when the utility actually even suffer. The utility can drop, and then it starts just memorizing the noises, outliers, and so on. So the insight of this work is that how can we actually utilize this paradigm or this insight to actually manipulate our pre-trained model to increase the memorization risk of the fine-tuning stage. So the idea is very simple. Given, for example, pre-trained model like this, before we do fine-tuning, we want to actually warm up the pre-trained model into a later stage so that during fine-tuning, it starts fastly move into the memorization stage. So that was the main idea behind our attack here. We're just going to accelerate our pre-trained model into this stage so that during fine-tuning, it starts memorizing the fine-tuning data. So that was the quick idea. So I'll show you. It actually increases the memorization risk of the fine-tuning data. And we also evaluated against some of these defenses, which we're going to introduce later on, the differential privacy-based training. And turns out it's not going to help these secrets that are actually memorized by this model. Okay. So that was very quick. I was just trying to give you an idea how we actually can do even stronger backdoor in the pre-trained model to actually amplify the privacy risk. So with that, I think we are actually at the time, and we are going to stop here and take a break. And then for next half of the lecture, we're going to introduce some of the enhancing technology, privacy enhanced technology, to see how we can mitigate some of these attacks. Any more questions for the 1 minute?
Thank you very much. You have any questions? No?
Sorry, stop it.
It's recorded already.
Oh, already?
Okay. I started it.
All right, welcome back. I hope I convinced you there are enough privacy vulnerabilities of building these AI models. And now for this second half of the lecture, I'm going to show you some common privacy enhancing technologies that we can use to improve the privacy of the models that we're trying to build. So to here.
No, I think
It's not.
you just have to press here once. No, it should work.
Okay. Okay, awesome. Okay. So in order to do this, I'll give you a quick overview. And then basically, I'm going to divide these techniques based on the pipeline of building the AI models. So there are techniques that we can use before the training, like sanitize the data and so on. And then during the training, we can do privacy enhanced training. And then there are also techniques that we can use after the model is being trained. For example, like machine learning to try to erase certain records from the model. So here's a pipeline overview. So again, this goes back to our pipeline. So before the data is used for training purposes, we can actually use a variety of techniques to help make our data more private. For example, we can do some simple techniques like deduplicate the data. So turns out for LLMs, for the text, if we do deduplication of the text, it actually reduces the memorization risks significantly. If the data is being deduplicated versus there are multiple records that are same being repeated in the training data, the records that are being repeated actually have a much higher memorization risk. So if we deduplicate the data, it reduces the memorization risk. We can also do data sanitization. So one of the recent works that we're currently working on with one of my students is that for web content, for our own web content, for example, we want to publish our web content, like our web pages and so on. And we want it to be readable by general public, by general audience, but we don't want it to be crawled or used by the model verbatim. So there are certain techniques that we can try to do to actually make the data unlearnable. So that's something we're currently trying to work on. For example, to inject certain invisible characters into the HTML content so that the model can still crawl it and use it for training, but it will not be able to memorize it specifically and regurgitate it later on. So there are actually quite some work along these lines to make data unlearnable, right? Even though it's still readable, but it's unlearnable by these large models. We can also do data synthesization. We can synthesize or generate synthetic data that mimics the original data, the distribution, the patterns, but it preserves the privacy. So our next talk is actually going to have a stronger focus on the data synthesization. I'm also going to introduce a little bit of a work towards this area, data synthesization. So in general, these are the techniques we can use before training. And then during training, we also have several different privacy enhancing technologies that we can use. One of the most commonly used, kind of like a standard practice these days, is something called differentially private training, or DPSGV. So this is really a technique to do training with some formal statistical privacy guarantee, so that after the training, we can ensure the model guarantees certain level of privacy in terms of the anonymity of specific record or member of the training data. There's also other techniques, for example, federated learning, that allows multiple parties to jointly train a model without revealing their private data to each other, kind of in a decentralized way. And there are also secure multi-party computation techniques that uses crypto techniques, also allowing multiple parties to jointly do a computation of output without revealing their data to each other. So I'm not going to go into details of many of these, but just as an overview so that you actually have a good kind of overall understanding. These are the techniques that can be used during training to protect the confidentiality of the data. And then finally, post-training, we can also do some kind of an output sanitization to sanitize the model output. So there are actually techniques that can be used during decoding stage, for example, with LLMs, right? During decoding stage, right before generating the content, we can do some kind of a sanitization. You can think of it as a filter to sanitize the output so that we make sure there's no private output that are being generated. There's also machine unlearning where we want to,
It will recover.
Okay. So machine unlearning is really the opposite of learning, where after the model is trained, maybe there are certain requirements that we need to remove the influence of certain data from the model. So that is what we call machine unlearning, which I'm going to go into a little bit of detail, give you some representative techniques. And there's also model auditing, where we can actually audit the privacy risks of a model, how much privacy it actually guarantees, and what is the exact empirical risk of the model, privacy risk of the model. So as you can see, these are different techniques at different stages. What I'll do before we go into some of the details of these is to introduce first a formal definition of a privacy guarantee called differential privacy. As you see here, a lot of these techniques actually can incorporate this statistical privacy guarantee. So we can do, for example, data sanitization with differential privacy guarantee. We can do privacy enhanced training with differential privacy guarantee. We can also do maybe output sanitization with differential privacy guarantee. So you can think of this differential privacy as a formal statistical framework that gives us a provable privacy guarantee. Once we can actually do some training or do some sanitization, we can show or prove that this technique guarantees certain level of privacy. It gives us a quantization, basically, of the privacy loss. So this kind of serves as a foundation for many of these privacy enhancing technologies. So that's what I'll do to introduce the foundation of this differential privacy, and then we move on to some of these specific techniques that we'll introduce. So differential privacy was actually introduced back in 2006 as a formal statistical privacy framework for releasing statistical data. So the main idea is, given a data set, and if we go through some randomized algorithm, for example, to share the data or train a model and so on, and then we get some output, in order to prevent the inference risk from the attacker, from the model back to the original data, we're going to make sure these randomized algorithms have certain probabilistic or statistical privacy guarantee. And this guarantee basically states that if we have a private data set D, and then if we have a neighborhood private data set D prime, and the only difference between D and D prime is one record, right? So this D has all the records, and this D prime has all the records except this one record. So they only differ in one record. And then we're going to guarantee this output of this randomized algorithm are actually indifferentiable, whether this output is generated from D or whether this output is generated from D prime. They are actually indistinguishable up to a certain statistical guarantee. So in that case, we can say this randomized algorithm satisfies differential privacy. So what does that really translate to is that now this attacker would not be able to differentiate whether this output is generated from D or D prime. In other words, the attacker would not be able to infer whether this particular record is used in the input of this algorithm. So statistically, this actually relates to the opt-in, opt-out principle. If we do a medical study, for example, usually we give you a consent form. We ask you whether you're opting, whether you're consented to contribute your data to this study, right? You can opt in or opt out. So this actually gives you a guarantee. Whether you opt in or opt out, the output will be the same. So we will not be able to infer whether your data is used in the training data or not. So this actually directly relates to the membership inference attack, right? If you remember, the MIA is that the attacker is able to infer whether a record is used in the training data or not. Here, the differential privacy guarantee actually directly guarantees the model is indistinguishable whether a record is used in the training data or not in the training data, or in the input or not in the input. Yeah. So it's a very nice privacy guarantee. And mathematically, it basically states like this. A randomized algorithm A is epsilon delta differentially private for two neighboring data sets D and D prime that only differs in one record. For all the outputs that's in the output domain, this inequality holds. So this inequality basically is interpreted as the probability of mapping from the input D to the output S, and the probability of mapping from the input D prime to the same output S. These two probabilities are almost similar, and they're only differing by a multiplicative factor of e to the epsilon. And then this delta is just a small additive factor, right? That guarantees a certain failure probability is smaller than delta. So if we look at this e to the epsilon, this epsilon basically is the level of the privacy or the level of the privacy cost. So if epsilon is equal to 0 and delta is equal to 0, what does this translate to? If epsilon is 0, that means these two probabilities are exactly the same, right? So that means doesn't matter whether my output is D or D prime, my output is the same. That gives us perfect privacy because the output is independent from the input. Right? So this epsilon essentially gives us the level of privacy guarantee. The smaller the epsilon, the stronger the privacy. And the larger the epsilon, the weaker the privacy guarantee, the higher the privacy cost, or the higher the privacy exposure, because the two probabilities can differ largely. Yes, question?
In case you're training, let's say, an algorithm,
yeah,
and then you are asking for something from the US.
Yes.
Then even if you can mask like the correct, even if you can make it private, it still has a lot of weights which point to the general person or people being named like so and so, which could be from an area because I mean they are of high probability in any case. Does this also account for that?
Actually, no. So this differential privacy is actually very nicely designed framework for training, for example, a typical classification model that has a bunch of records. And one of the strong assumptions here is that we're assuming all the records are independent from each other, so that whether this record is in or out, our model is indistinguishable. However, in the LLM case, it becomes very tricky because all the samples are kind of overlapping with each other. There's strong correlation between different sentences, different samples, different content. So the actual guarantee of this differential privacy for LLMs is actually not very well understood. It's a very open question, open research direction. We can apply the differential privacy for training LLMs or fine-tuning LLMs, but in terms of the exact privacy guarantee or the privacy risk kind of defense is not very well understood. So exact verbatim membership inference, you may actually protect against it. However, in terms of extraction attack, as we mentioned earlier, we can probably still extract verbatim data from it, or a certain portion of the data from it, or certain secret from it. Or in your the case you were talking about, maybe their records all from US, they are all correlated. We would not be able to guarantee even if we can guarantee like a certain record, but if it's a correlated record, we may still infer additional information. Yeah, so that's a, it's a very nice mathematical framework, but in terms of its application and actual defense for LLMs, it's still very less like understudied, and there's a lot of open questions. So this is the mathematical requirement. In order to achieve this, the typical way of achieving this is to adding some randomization into this randomized algorithm. So for example, Laplace noise or Gaussian noise to the output so that we can actually guarantee the output is indistinguishable. Now, if we want to apply this to the model training, there's a technique called differential private SGD, which we're going to go into detail a little bit. So this differential privacy, as we mentioned, even though it has limitations, but still is used as kind of like a standard, industry standard almost these days for data release and data sharing. So during COVID, for example, a lot of companies like Google and Meta, they actually released their data set using differential privacy to generate aggregated data and release it for the public to use for public health research. And our next talk is going to talk more about this using differential privacy to do the data release. So, but in this case, what we're going to focus on is to apply differential privacy for model training, right? So if we have some data, we want to train a model, how can we guarantee differential privacy of the model? Meaning a data set has one record without a record, this model is indifferentiable. So the main idea is called differential private SGD stochastic gradient descent. The main idea is to adding some noise to the model training process. So in the model training process, typical way we do is the SGD stochastic gradient descent, right? We take a batch of the record for each epoch. We take a batch of the record, we compute the loss for each of the record, and then we compute the average loss, and then we compute the gradient for each of the record, and we compute the average gradient, and then we use the gradient to update our model parameters, right? So that's our SGD process. Now, the main idea behind DP-SGD or differential private SGD is to add in some noise to the gradient, because the gradient is derived from the original records, right? Because the loss of the record corresponding to the ground truth. So it's computed based on the original record. In order to protect the original record, we need to somehow perturb the gradient so that we can actually hide the presence of this record. And the way we perturb it is just to add in some noise to the gradient. Now, the main idea behind differential privacy is that we need to add in sufficient noise to have that guarantee, right? So the noise is usually calibrated based on the sensitivity of the input. The sensitivity of the input typically means if I change the record or if I remove the record or versus in adding this record, how much the final model would change, or in this case, how much the gradient would change. But in this case, if we add in record versus remove a record, or if we change the record value, how much would the gradient change? Can we bound the record? Can we bound the gradient? Not really, right? The gradient can change, can be unbounded. The gradient can be very large versus very small. So we don't really know how much the gradient can change. So in order to actually have this differential privacy guarantee, one small trick we do is we simply apply an artificial bound on this gradient. So we clip the gradient. Then we know the gradient will be bounded. Right, so that is the main idea behind this differential private SGD. We do some gradient clipping, and then we add noise to clipped gradient. So that's the main idea. So here, it just illustrates the whole process. We take a mini batch of the training samples, and then we compute the per sample gradient. And you can see maybe some of them have a high gradient, some of the samples have a low gradient. And then we clip them based on a maximum gradient. And then we scale down the rest of the gradient proportionally based on the maximum bound. And then after that, we compute the average gradient of the batch. And then we apply a perturbation by adding some Gaussian noise that's calibrated based on the bound. And then with that, we have a private gradient. And then we use the private gradient to do the model update, right? So we just update our model parameters using this private gradient instead of the original gradient. So by doing this, we can mathematically prove the level of privacy, which corresponding to the epsilon and delta of the model. We can say, okay, this model is epsilon delta differential private. And this typically relies on the clipping bound and number of epochs and so on. All of these parameters contribute to the privacy level. Yeah. Any questions? So this would be, I think, one of the main takeaway of this lecture. Even if you don't know the details, but at least this exposure or this knowledge of this DPSGD, I think will be useful, right? When you talk to people, okay, I'm building a model and maybe people question, okay, there's actually privacy risks. You can always say, okay, there's a way to make the model private, which is DPSGD. We can always train a model using DPSGD instead of original regular standard SGD to make the model differentially private. But then, of course, the caveat or the trade-off, the limitations here is that we are adding noise to the gradient. So the model, you can imagine the model will not be as accurate because the gradient is being perturbed. So your model either take maybe longer time to converge, or the model is not as accurate because your gradient is not accurately reflecting your original gradient, right? So this is a privacy utility trade-off here. There's always no free lunch, even though in the beginning we talked about the privacy and generalization capability are aligned, but in terms of the exact technique, because this technique introduces noise into the gradients, so there is actually a privacy utility trade-off. So the more noise we add into the gradient, the better privacy, the smaller the epsilon, but also maybe the more we suffer in terms of utility or accuracy of the model because the gradient is more noisy. So there's this typical no free lunch, typical privacy utility trade-off here. Okay.
So the only thing here we are changing is the optimizer.
Yes, we're changing the optimization process, right? During the
No change on the data.
no change on the data, exactly. So this is just for the training. Now, if we think about data sanitization, we can actually sanitize the data or generating aggregate data or generating synthetic data that mimics the original data and make it differentially private. In that case, I'll show you an example later on. We can actually generate synthetic data, changing the data, generate synthetic data with differential privacy guarantee, and then use that data to train our model. That's also one way to do it. But in this case, we can, whatever model, we can actually train it using DPSGD to ensure the model is differentially private.
And the only difference between DPSGD and the normal SGD is the clipping and the noise.
Exactly. It's a very simple, straightforward technique. But of course, there are a lot of optimization that happen later on to kind of enhance the privacy utility trade-off. But the vanilla version of DPSGD is very simple. It's just clipping and perturbation. Yeah. Yes, questions?
Is there a way people determine how much impact would the amount of clipping and noise that we're adding have on the convergence timeline and also the performance of this model?
Yes. So there are a lot of studies along these lines, and the typical trade-off is this. So the typical trade-off is per iteration, we're going to add in some noise, and that noise translates to certain epsilon guarantee. And over multiple iterations, there's this composability property of differential privacy, basically adds up the privacy cost. So the more iterations we have, the higher the privacy cost. Right? So this is the typical trade-off. So for each iteration, the smaller the epsilon, the stronger the privacy guarantee, the more noise we need to add into the gradient. And then the more iterations we run, the higher the privacy cost. So essentially, it's a trade-off. If we do the higher noise or the clipping bound, you also mentioned the clipping bound, right? So there's also trade-off in terms of clipping bound. If we give it a lower, like smaller clipping bound, we can afford to add in smaller noise because the sensitivity is lower. However, the more strict, more aggressive clipping bound would clip the gradient more. It will introduce the gradient approximation error, right? So it's also a trade-off in terms of the gradient approximation error versus the perturbation error. So there's no like exact optimal values. So a lot of times these are depending on the tuning, like a hyperparameter tuning. What is the clipping bound? And then there's actually more recent works doing auto clipping, like automatic clipping in terms of the clipping bound. So there are like a lot of active research going on in this area, how to enhance the trade-off, how to do this automatically, and so on. Yeah.
If I can determine, is there a relationship that I can determine between the epsilon or the noise that has been added and then the output performance? And I can say, okay, for this particular data set, I know if it doesn't perform to the level, I can determine what the epsilon is or how much noise is that. Can I retrace the steps back to get the original data and then people should be very careful on actions, demographics?
Yeah, that's a great question. So the nice thing about this differential privacy guarantee as versus, so in the past, before the differential privacy came out, there are a lot of input perturbation work. Right? So for example, you can just perturb your values and then train your model. And then from that model, turns out you can actually reconstruct the original data. Now, in this case, the nice thing about differential privacy is that it actually adds noise on the output, in this case, on the gradient. So you can actually think of the model is actually being perturbed. And from the model, if you want to reverse and figure out the membership, right? So there is a mathematical guarantee. Essentially, this mathematical guarantee tells you the inference risk. The epsilon is the inference risk. So the epsilon is typically published. Right? If I train a model, I tell you, okay, this model is epsilon delta differential private. The exact privacy risk level is corresponding to the epsilon. So it's not an absolute guarantee. It's not an absolutely bulletproof guarantee, right? It's still, there is privacy leakage, but the leakage is bounded by epsilon. So you can actually still do the reverse engineering, but I'm telling you, the inference risk is bounded by the epsilon. Does that make sense? Yeah. More question there? Okay. So yeah, if you can ignore you can actually feel free to ignore the rest of the talk, but just take away from this lecture, the DPSGD, if you take this away from the lecture, I consider it a success, right? So you can tell people, okay, you can train your model using DPSGD and make it private. Even though there is still privacy utility trade-off, but this is the standard commonly used technique for training a model with privacy.
No, I got a question.
Yeah, okay. Okay, of course, there are a lot of things going on in terms of making it more better trade-off and so on. Also, how to make it efficient. If we do this differential private training, you can see because of clipping and perturbation and so on, it also adds computation costs. So there are a lot of open challenges how to do this, both improving utility and improving the efficiency. Okay, so that hopefully gives us an overview of the potential privacy notion we can use and privacy technique we can use. And now I'm going to show you some techniques for each of the stage of this AI pipeline. Before training, we can do data synthesization, and during training, we can do the privacy enhanced training, and post-training, we can do the machine learning. So data synthesization, I want to just show you one work that we recently do. So data synthesization is a very general way of generating synthetic data. We also mentioned earlier, right? Given some original data set, we can always generate some synthetic data that mimics the distribution pattern, captures the pattern of the original data, and then use this synthetic data to do our model training. So for example, here we have some sensitive records, maybe corresponding to people's income and maybe health records and so on. And then we can try to generate a synthetic set of data. And now we can use this data set for model training and so on. So in fact, these days, a lot of these big companies, they are actually very, very interested in generating synthetic data to train the model because they want large amount of data, right? And the private, especially tabular data, because they are very limited, so they want to generate more synthetic data and use that to feed their data-hungry models. And as we can actually see here, what I want to argue is that if we don't do this carefully, there are a lot of methods we can actually use to generate synthetic data, like marginal-based methods or generative adversarial network, like GAN-based models, or using LLMs to generate this model. And if we don't do this carefully, what I want to argue is that these generated synthetic records might also reveal the original data, right? And maybe in some cases, it just duplicates some of these records, right? In those cases, that's the best utility of this synthetic data, because we want this synthetic data to mimic the original data. That's the utility, right? But on the other hand, if we don't do this carefully, the synthetic data can actually reveal the original data. So that's why we also want to do model or do the data synthesization with the differential privacy guarantee. So essentially, we want to build these generalization models or the synthesization models with differential privacy guarantee. So how can we make the data synthesization model or generation model with privacy? What would be the technique we can use to make it private?
So I don't know the technique, but is there no step at the end to verify that the sanitized data conforms to some
synthetic.
qualities.
Yeah.
I mean,
Yeah, we can do some auditing, right? So that's fine. We can do some verification, auditing, or check to see if this data reveals original data. Yeah. But what about the process itself, right? So there is some generation module here. How do we make this generation, for example, satisfy certain privacy guarantee, like a differential privacy?
Change the optimizer for the GAN itself.
We change the optimizer for the GAN, exactly. How do we change the optimizer? What is the technique we can use, or the algorithm we can use? DPSGD, right? Exactly. So that is the only thing I want you guys to remember, or the least thing I want you guys to remember. So if we want to make this model differential private, we can apply DPSGD. Yeah. So my student tried this. So so here, this is the latest approach of generating tabular data using LLMs. So it turns out there are a lot of techniques in the past using GAN models and so on. But then the latest thing is to use LLM to do everything, right? So this thing is using LLM to generate tabular data. So the idea is very simple. Given a tabular data set, we have some age, education, occupation, and so on. So we're going to represent the tabular data using text format. So convert it into age is 23, occupation is clerical, and income is this, and so on and so forth. So now we have these sentences. And then we're going to feed these sentences to a LLM and fine-tune the LLM using the language modeling task. Basically, ask the LLM to predict the next token given the previous tokens. So by doing this fine-tuning, the model is actually learning these correlations between these attribute values. And after the fine-tuning, then given some prompt, the fine-tuned model can be used to generate attributes. So this is one way to use the LLM to do the tabular data generation. But then again, as I mentioned, this model may not be private, right? So it may actually generate some records that actually duplicates the original attribute values. So how do we make it differential private? We can make this fine-tuning process with DPSGD. Right? Instead of using SGD, we can use DPSGD to fine-tune the LLM. And my student tried this, and turns out it does not work very well. As I mentioned, there's always privacy utility trade-off. So when we do the DPSGD in the fine-tuning process, and turns out this is the evaluation perplexity, right? So this is the training epoch, and this is the format compliance. So it turns out the generated values, they actually violate the format. So when we use LLM, we want to generate the sentences that looks like this. So we can convert them back to the tabular data, right? But before we apply the differential privacy, it generates these texts very well, the formats very well. But after we apply the differential privacy using DPSGD, and all these templates get messed up, the format gets messed up because of the noise in the gradient. So it does not generate these nice formats anymore. So we won't be able to convert them back to the tabular data. So this is our challenge here. So this basically shows you a lot of times DPSGD is a powerful tool, but if we just apply it, many times it would not give us good utility. It would have a big trade-off between the utility and privacy. So this is one of the cases, especially when the model is becoming big and the model has a big number of parameters, the cost of the privacy, accumulated privacy cost becomes large. And then in this case, it completely ruined the generated format and does not have any utility at all. So how do we actually get around or improve this? So one of our idea is that because this ruins the format, so if we think about the generation task, we want to learn the format, then we also want to learn the correlation of the values, right? The patterns of the values. And the format is actually not dependent on private data, right? So if we only care about generating the correct format, evaluation is, education is this, age is this, occupation is this, these can be actually learned from non-private data. And the only place we need to inject privacy is when we try to learn these values, 59, the age of 59, the income is 60K, and so on and so forth. The only place that we care about privacy is the values. So then our idea is, why don't we separate the learning into two stages? The first stage, we just learn about the format. train the LLM so that it can generate the right format. And then the second stage, we fine-tune LLM to learn the actual values or correlation between the values. And the first stage for the format learning, we don't need privacy. We don't need differential privacy, right? The second level, second stage, then we can use the DPSGD. So that is the main idea. First, we just generate some random tabular data and with the attribute names and some values. These values can be random values. And then we just fine-tune our model, LLM, and try to learn the format. And at this stage, we don't need any differential privacy. And then the next stage, we use the actual sensitive tabular data and then do the actual fine-tuning. And this stage, we can use the DPSGD to do our fine-tuning. And then finally, we can actually do the final generation. So the idea, there's some small tricks we use here. When we do DPSGD, we actually give a different weight for different values and different format. So the model learns to generate the values more correctly and so on. So anyway, so the reason I want to show this work is just to show you some insight that there is an inherent trade-off between the privacy and utility when we apply DPSGD. And a lot of times there are techniques to kind of help us improve or enhance the privacy utility trade-off. One particular idea that is being commonly used is to leverage some kind of multi-phase training or some hybrid data training, right? Using public data to learn some things and then warm up the model. And then at a later stage to use DPSGD to train a model using private data and so on. So this is a very commonly used technique to leverage the warm-up model or pre-training or public data to improve the privacy utility trade-off.
But how to make sure that the schema of this public data align with the schema of the private?
Oh, so yeah, in this case, in this particular case, the schema is very simple to obtain, right? So we assume we know the schema. So the first phase is just trying to learn the schema to let the LLM to generate the right attribute names and so on and so forth. Yeah, instead of using the private values. Yeah. But there are other work that trying to, for example, improve privacy utility trade-off, where they may actually use hybrid data, use kind of both public data and private data, and try to do a lot of kind of tricks to align the private data learning and so on. For example, one idea is to use public data to get a gradient, and then use that gradient to calibrate the gradient that's learned from the private data, so that in a way it's kind of denoising the noisy gradient. So the insight behind it is the same. Basically, try to leverage some of the public data to help with the private training part. Yeah.
I mean, you probably said this, but I missed it. So why we don't add noise to the sensitive data and just train it with the non-SGD?
Yeah, so that's another way to do it, right? So if we have this data set, we can add noise to this data set. But then on the other hand, it's not easy. That's also like an open question, how to best add noise to this original data, right? So this itself is like a chicken and egg problem. So this technique basically allows us to generate a synthetic version of this, right? It's one way to actually generate a synthetic version. Now, once we have the synthetic version, we can use the synthetic DP version to train whatever master is. But there are certain techniques, you are probably going to mention some, to generate like aggregate data of this with differential privacy and then sample data from that aggregated distribution and so on. That's alternative ways of doing it. Yeah. Other questions? Yes.
Let's say that you're trying to synthetically generate location.
Yeah.
Do the current approaches in your idea already try to account for, like, if we are adding noise to these data, we have to make sure that they actually follow the certain pathways on real maps?
Yes, exactly. So that would be our next talk. But we are actually also trying to apply this idea to actually generate trajectory data in collaboration actually with our next speaker. So it turns out it is actually difficult. Without differential privacy guarantee, actually we were able to get very good performance. But once we add in the differential privacy, it becomes very tricky because the trajectory data is actually sequential. So in order to kind of still capture or preserve the temporal patterns with the differential privacy is actually very difficult. So we have some other works that using GAN models to generate trajectory data with differential privacy, but then with this LLM-based approach, we were just able to do it in a vanilla non-DP way.
But with DP, there's still a lot of work to be done in order to make it reasonably performing well.
Problem could also be like we interpreted in this manner that our current like frontier LLMs are supposed to be these expert reasoning systems, but also contain a lot of word information. But if we rephrase it as let's just make the LLMs reason on real world data, so that it doesn't need to memorize all of the pathways, but it just like reasons over
The
any
actual
given
patterns
pathway
generate
right now.
the.
Yeah,
Yeah.
This can make a difference.
I think so, yeah. I think that actually exactly points to the direction we're currently trying to investigate. So in our previous effort, we are using this fine-tuning approach, right? So as you mentioned, this fine-tuning approach is really just learning the next token prediction. So it's learning the kind of syntactic pattern, right? What we really want is for the model to learn the actual pattern or kind of activity chain behind the actual trajectory, right? The syntactic, but really the semantics behind it. So right now we're actually exploring the approach using the MCP to do the kind of learning of the activity using some feedback mechanism so that it actually learns the reasoning behind how this trajectory is generated. So that was actually the approach we're currently trying to investigate. Yeah, exactly. I think kind of aligns with the insight you were mentioning. Yeah, the reasoning versus just the superficial pattern learning. Yeah, which is not very good. Yeah, especially when the sequence is long, the long sequence, long context, it kind of becomes difficult for the LLM to learn. Yeah, great question. Okay, so that's the technique, and then here's just some quick results. I think this is not as important, but I can quickly show you. Just basically shows this LLM with DP approach actually outperforms the current baselines that using marginal approaches, using GAN approaches, and so on and so forth in terms of the utility of the or fidelity of the generated data set. So that gives you some idea how we actually can generate synthetic data before training, so that now we have a data set that we can actually use for training a variety of downstream tasks for a variety of purposes. Now what I want to show you is to do some privacy enhanced training for LLMs in particular. So as we already mentioned, for privacy enhanced training, we can use DPSG. Yes, go ahead.
But is using the DP affecting the overfitting?
That's a great question. So there are works actually studying using DP as a regularizer for improving the generalization capability. So there is some correlation, but then in most cases, DP still have a negative, more stronger of a negative impact in terms of affecting the utility because of the noise. So it's a very tricky in terms of amount of noise you add. Right? So there may be like a tricky point where you just add this amount of noise so that your model is more regularized and have a more stronger generalization capability. But the privacy guarantee might be weak. So if you want a reasonable privacy guarantee, then it actually hurts the performance because of the noise.
You have like a measure of memorization other than overfitting since they are correlated.
Exactly.
Can we say this model can memorize such and such for a certain measure? Are there measure nowadays for memorization for a model?
Can you say it again?
I mean, how you characterize a certain model with memorization?
Right.
Yeah. Is there a measure for memorization?
For memorization, yes. What we just learned. So what metric can we use to actually quantify or empirically evaluate the memorization risk of a model? What can we use? Well, we just introduced in the first lecture.
The binary membership.
Exactly, membership inference attack. So that's what we meant by using the MIA, the membership inference attack, as an auditing tool. So this differential privacy gives us a kind of worst case bound epsilon. And then if we were to, for example, do the MIA attack on the model, we can actually get a lower bound of the epsilon, like empirical bound. So the MIA risk actually corresponds to the epsilon, like lower bound of the epsilon, because it depends on the power of the attack, right? In a lot of cases, when we do the MIA attack, it's actually not matching the epsilon guarantee. The epsilon is like a worst case guarantee. it basically means theoretically, the attacker can actually infer the membership of a record up to this risk level, epsilon. But empirically, in practice, when we do the MIA using whatever techniques we have learned earlier, and usually we get a much smaller epsilon. It means we do not have as strong of an attack, right? So, but that gives us a lower bound. So that is exactly what I meant by privacy auditing. So we can use MIA as a metric to audit our model in terms of the empirical privacy risk or memorization risk that the model has. Does that make sense? Yeah. So this is actually how it connects. The MIA is actually a empirical quantification in terms of the privacy risk. But this epsilon here is just a theoretical bound of the risk. Yeah. Okay, so now if we have the LLM, as I showed you, we can use DPSGD for doing the privacy enhanced training, right? But then, as I also showed you, it can hurt the utility quite a bit. So what we wanted actually to study currently is that we have one work recently that we're trying to say, can we have actually some empirical, more lightweight mechanism that would allow us to do the private training? Maybe it does not have formal differential privacy guarantee as the DPSGD does, but then it would have better privacy utility trade-off, right? Because our goal is to train the model so that it has good utility and also has good privacy in terms of membership inference prevention or protection, right? So what we did recently is a work that will be published soon, tokens for learning, tokens for unlearning. Basically, we're trying to mitigate the membership inference attack when training these large language models by using a kind of dual purpose training objective. So the main idea was inspired, again, coming back to this training stage, is inspired by this training stage memorization evolvement, right? So as we mentioned earlier, during the training stage, in a very early training stage, the model is learning the overall patterns, and then it gradually moves on to the memorization, and then finally it moves on to the overfitting stage that only memorizes noises and stuff. So our main goal or question we want to ask is, how can we actually, during this stage, how can we actually learn without memorizing? Right? We want to learn the general patterns, but we don't want to memorize the specific, sample-specific information. So that is our main goal. And there are some existing work. So one work, which is now widely kind of recognized as useful, is something called goldfish. So this idea is very simple. So traditionally, when we use a standard like causal language modeling loss to train our language models, we use the, this is the CLM loss, the traditional loss. So basically, given each prefix, we try to predict the next token, and then we get the log perplexity and we aggregate them and then divide it by the L, which is the total number of tokens. So this gives us the average token loss, right? So we basically use the CLM loss to train our language models to try to learn the autoregressively the next token. And if we train the model like this, the model does have memorization risk. So in this case, if you ask the model, the Harry Potter Mr. and Mrs. Dursley and blah, 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 and then the model actually would finish the sentence exactly verbatim. That's kind of used, probably used in the training data, the Harry Potter book. So it's going to spit out the exact sentence from the training data. And in order to mitigate this memorization risk, so one recent work is called goldfish loss, is using a very simple idea. What it does is that instead of using all the tokens for the loss aggregation, so it simply masks out some tokens. So it just takes a random subset of tokens and take their loss and aggregate them as the final loss. So they call it goldfish loss because goldfish kind of forgets things, right? So they are trying to take this loss and then use this loss for training. So instead of optimizing the model to trying to predict every token accurately, now the model is optimized to train to predict certain number of tokens accurately. And turns out by doing this, the model actually is learning not to memorize exact sentences. So this is the illustration of the result of this goldfish loss trained model. So using the same prompt, the model is actually saying they were not one of those horrible families. So basically, these are not regurgitated verbatim sentences from the trained model, from the training records. It will be rephrased and so on and so forth. So this exactly shows the difference between the goldfish loss-based and the standard loss-based. And then the y-axis is the memorization score. So you can see the standard loss-based, the memorization score is very high, but the goldfish loss-based, the memorization is very low. I mean, not very low, but slightly lower. So it still memorizes, but the memorization risk is much lower. So this is the main idea behind the goldfish loss. It's very simple, right? And now when we were looking at this, we were thinking, okay, so this is just randomly selecting a set of tokens. So can we actually select these tokens in a more smart way, right? And we talked about the MIA on the LLMs, right? So we know that certain tokens may actually contribute to the MIA signal differently. So can we actually figure that out and then doing learning on those like tokens that represent the patterns, but trying to forget or mitigate the memorization on those tokens that are being specifically memorized. So that is our main idea behind this. So what we did is to do some analysis in terms of the memorization of different tokens given a training sample. So this is a training sample. We can see here, this is a query sample. And then if this, so we first did an analysis in terms of the memorization signal of different tokens in this sample. And this memorization signal essentially is the MIA signal. We talked about the MIA signal earlier, right? So given each of these tokens, we can actually test or get their perplexity loss and then aggregate them. And then overall, this would be the MIA signal of this sample. So we did this for a bunch of member samples and a bunch of non-member samples, and then looked at their MIA signal. So we can see they are actually kind of separated. So there are members that their overall MIA signal is much lower, meaning their general loss is lower. And the non-members, their loss is higher. So this actually matches what our observation is in the previous half of the lecture, right? Because the sample are already trained, the member samples are already used in the training data. So their MI signal or the calibrated loss in this case is actually smaller or lower. So by the way, these are actually calibrated. Remember the calibration we talked about. One is the reference model-based calibration, one is the neighborhood-based calibration. So here, we're using a reference model-based calibration. So this is the calibrated loss for the member sample versus non-member sample. So you can see they're somewhat separate from each other. The members are generally have a lower loss. So what we are actually doing is to say, can we actually utilize this fact, right? Because different tokens may be actually memorized differently. So for those tokens that are memorized, can we actually try to reduce their memorization instead of increase their memorization? So we did this token analysis, token level analysis. So during each training epochs, these are different tokens sorted by the token index. And the level is their MIA risk or loss. So you can see different tokens at different training stages, they have different loss level, different MIA level. So the higher the loss, it means the token is not as necessarily as memorized. The lower the loss for that token, it means that token is already memorized by the model. So our idea is, can we actually, for those memorized tokens, we want to reduce the memorization. For those tokens that have not been memorized, we want to increase their learning. So we divide this learning into two objectives, right? So given the training sentence, instead of trying to optimize their loss, minimize their perplexity log loss altogether, we are actually dividing them into two types of tokens. One kind of tokens are the red tokens. These tokens are the tokens that have very small loss or MIA signal. That means the model is already memorizing them well. And for these tokens, we actually want to reduce their memorization. So we want to actually maximize their loss. And for the remaining tokens that are not being memorized by the model as well or learned as well, we want to actually use the regular training loss to reduce their token. So sorry, this green one. So we want to actually minimize the loss. But for the memorized tokens, we want to maximize their loss. So the intuition behind this is that we're doing token level kind of specific learning, right? For some tokens, if they're already memorized, we actually want to increase their loss so that they're not being memorized as much. And for the remaining tokens, we want to do the regular learning. We want to minimize their loss so that they're learned better by the model. So it's kind of like dual purpose learning, right? So we want to both improve the utility of the model, by training on these remaining green tokens, but also we want to mitigate the memorization risk by reducing the memorization of those already memorized tokens. Does that make sense? So this is our dual training purpose. So we actually combine these two losses so that we can do both mitigation of the memorization and the utility based training. So it turns out this very simple mechanism by doing this dual training actually improves utility and privacy trade-off. Yes?
But that means calculating the MIA for each token, and this is quite expensive, especially with long text.
Yes, so for doing MIA on the LLMs, it is quite expensive because we are actually taking the loss of each token based on the prefix, and then we aggregate the loss as the overall loss signal, and then we use that loss signal to do the MIA. Yeah. So the MIA attack itself is expensive. Yeah. And for this training, so if your question is related to the training, yes, for the training, it does add a little bit of computation cost because for each of these tokens, we're actually, so we're not doing the real attack here, we're just doing the loss-based attack, right? So the loss-based attack itself is actually fairly efficient because we're not doing the shadow model training or anything like that. We're just doing the loss-based attack. So we're using the threshold, right? For example, given the threshold, if the loss is smaller than a certain threshold, we say these are kind of memorized tokens. If the loss is greater than a certain threshold, we say these are hard to learn tokens. We want to focus learning on these hard to learn tokens. Yeah. Great. So the main intuition is basically, do these two kinds of, separate these tokens into memorized tokens versus that hard to learn token so we can do different purpose for the training. So with that, I want to just show you some results. So here we trained these different models, different LLMs, and then so for the different columns, the PPL perplexity basically shows the utility of the model. And then for the next 4 columns, it shows the different MIA risk. Using the different MIA methods we have introduced. Right? So one is the loss-based attack, one is the reference model-based attack, one is the min K-based attack on the LLMs, taking the minimum K percentage of the tokens to do the MIA. And then there's also zlib, it's like a normalized attack, like an alternative attack. So these are 4 different kinds of MIA attacks. And we can see the perplexity, the lower, the better utility. And in terms of the AUC for these different attacks, the closer it is to 0.5, the better the privacy, right? Because the membership inference attack is like a random guess. If it's 0.5, it means member or non-member is like a random guess. So 0.5 is the best, corresponding to the best privacy. So then you can see the base model is the model that without fine-tuning on the private data. So it has very bad utility, but very good privacy because it's not trained on the private data, right? So it has close to 0.5 AUC. And then if we do the fine-tuning of the model using our private data without any privacy defense, without any privacy protection, you can see the model utility is very good. It's very low perplexity. But on the other hand, you can see the AUC for the MIA risk can be very high, especially the reference model-based case in this case. Right? Again, this is just another data point. The reference model-based attack is much stronger than the regular loss-based attack. So in this case, it's actually close to 100%, which means we can almost accurately determine whether a sample is a member or not. So this is without any privacy protection. And then we are comparing our dual learned strategy with the 2 techniques. One is the goldfish loss that I introduced, and then the DPSGD, which is adding differential privacy during the training process, during the fine-tuning process, using the gradient perturbation and so on. So we can see that in this case, by comparing with these 2 baselines, the dual learn approach maintains the utility while still pretty low perplexity, but also enhances the privacy or protects the privacy leakage by achieving close to 0.5 AUC. Right? And if we look at the DPSGD, it also has pretty good privacy protection, but on the other hand, it does suffer in terms of utility because of the noise we added to the gradient process. So if we look at this kind of Pareto optimal approaches by looking at both the model utility and the privacy risk, we can see the lower the perplexity, the better utility of the model is, and then the lower AUC attack, the better privacy it is. So we can see the dual learn strategy actually was able to achieve a good Pareto optimality. in terms of achieving both good utility and strong privacy protection. And on the other hand, the DPSGD, which is the red ones, you can see it has a very strong privacy protection, but on the other hand, it suffers the utility. So this is just, I wanted to kind of show you the insight behind this. Sometimes the empirical approaches may get us a good trade-off in terms of utility and privacy, but it does not have a theoretical guarantee. On the other hand, the DPSGD approaches gives us a theoretical guarantee. However, it does have a utility trade-off. Okay. Questions? Yes.
Usually, publicity does provide a general sensitivity of foundation model by the last policies.
Yes.
If we evaluate this on specific tasks, downstream tasks, many of which do rely on memorization, then would we see an impact on that?
Yeah, that's a great question. So this is a general utility. We do have some results that have the downstream tasks, evaluating utility using downstream tasks. So I think our understanding is that a lot of the downstream tasks do not rely on the memorization. So memorization mainly corresponds to the data leakage risk. And a lot of the general tasks do not rely on the memorization.
Calculations or fact, based on fact that you want to look at the president of X country is, that still requires some level of remembrance that this is what it is.
That's a great question. So in a sense, I think there's a subtle difference between the exact verbatim memorization versus the knowledge, right? So if the model is trained well, hopefully the model would remember those knowledge, would remember those facts, but not verbatim sentences or sample specific information. Like this person has this phone number, has this social security number, and so on. So in terms of the general knowledge, like the president of the country and so on, hopefully those are the knowledge that it will be learned. It will be learned by the model, but not the sample specific information. But that is a very tricky, I think, fine line between that. So I think you're definitely right. It probably takes much more comprehensive and rigorous evaluation in terms of those different tasks and benchmark data sets and so on in order to say this technique really helps. Yeah. So that's a great point. Yeah.
Then what should we choose between the empirical one and the theoretical one? You use a pretty simple, straightforward empirical design to beat the theoretical one.
Right. So I think there are several interpretations behind this. So first is that the DPSGD gives you a theoretical guarantee. So the theoretical guarantee is like a worst case guarantee. Right? So empirically, we may not need this stronger or strict guarantee. Right? So there's a trade-off in terms of, in practice, we may want a reasonably guaranteed privacy risk that can be empirically audited, right? But good trade-off. So that's the trade-off between kind of theoretical guarantee and empirical guarantee. That's one thing. And the second thing, I think it also, there's a good argument that I want to make here is that even the DPSGD gives you the theoretical guarantee, it does not necessarily translate to the empirical guarantee that well, especially for language models, because the membership inference attack is based on specific samples, but then different text samples may have overlaps and so on. So this fundamentally actually is in conflict with the assumption of differential privacy. So differential privacy does assume the independence of different records in a database. So we need to take this differential privacy guarantee with a grain of salt, because even though it is a theoretical guarantee, but it does not directly translate to the empirical risk. So that's why we also see these kind of differences between the empirical and the theoretical guarantee. So when we do the privacy auditing, there are a lot of work going on in terms of privacy auditing to try to figure out the empirical risks using MIA, for example, to try to estimate the epsilon. So there's currently a huge gap between the estimated epsilon, empirical epsilon, and the theoretical epsilon. So that basically means either the DPSGD is too strict or our MIA attack is not strong enough yet. So we can come up with even stronger MIA attack. So those are the limitations of this, right? So all of these are based on the current MIA attack, but maybe there's stronger MIA attack that actually shows a higher risk. Yeah. So yeah, so those are the trade-offs. Good question. Yeah. Okay. So this figure I wanted to quickly show you also kind of verify the fact or the observation that we have made early on that when the model overfits, the memorization risk increases. So this actually shows this. The orange one showed the difference between the training accuracy or training loss and the test loss. So it's very small. That means the model is not overfitting. That translates to a very low privacy risk. Now, for the model that's trained and fine-tuned without any privacy protection, you can see the blue line right here is the training loss. And then the dashed line above there is the test loss. So you can see there's a huge gap. That means the model is actually overfitting the training data. That actually translates to a very high privacy AUC or privacy risk for this model. So this again confirms our intuition and observation that a model overfits tend to have a high memorization risk. We also tried this with our backdoor MIA attack. That's a stronger version of the MIA attack. It also shows the dual learn actually has a stronger protection. Okay, so that hopefully gives you some idea how we can actually enhance the training using some privacy guarantee, either empirical guarantee, like more lightweight, or with differential privacy, but with stronger theoretical guarantee, but maybe a higher utility cost. Now I'm going to use the rest of the time to try to briefly tell you about some techniques that can be used post-training. Right? So this is called something called machine unlearning. So what I'll do is to give you a quick overview and then introduce one of our recent works on contrastive unlearning, and then finally talk about unlearning of the LLMs. So the reason we want to do unlearning is usually motivated by the right to be forgotten. So privacy regulations like GDPR, Europe is really good at privacy regulations. So for this, there's a specific statement that states that individuals, we have a right to ask the organization a complete removal of our personal data. Basically, we have the right to be forgotten. Right? So from a data set, and also this means whatever model that trained on this data set should also forget our record, forget our data if we make this request to be forgotten. So that means the model needs to kind of unlearn this data from this model. So what is the most naive way of forget a data record from a model? The most naive way is to retrain the model without a record, right? But then that's going to be very expensive. So the main motivation behind machine unlearning is to somehow update the model without training the model from scratch so that we achieve the similar effect as if the model has forgotten the record, or as if the model has been retrained on the records without the unlearned records. So this is the overview of the machine unlearning goal, where we have the original training data set, we train a model, theta original, and then if we now have a set of records, de-unlearned, that have requested their data to be unlearned or forgotten, so we can retrain the model by using the remaining or retained data, and now we have a retrained model. So our goal for the machine unlearning is to somehow unlearn the model by taking the original model and do some unlearning, update of the model, so that we get an unlearned model that hopefully behaves almost exactly the same or similar to the retrained model. Right? So our goal is to achieve this model update so that the model actually forgets the unlearned records. And the way we can evaluate this is the several aspects or metrics. First of all, we want to maintain the performance of the model. So after unlearning, we don't want our model to perform poorly on the remaining data. We want our model to still perform well on the remaining data and on the test data. So that's the model performance. And then secondly is we want the model to unlearn the records effectively. That means we want the model to completely erase the influence of the unlearned records. And in order to do this, we can actually check the model accuracy on the forget data set, and hopefully it would perform similarly to the retrained model. And secondly, we can also use membership inference attack, the MIA, as we talked about, to verify whether this record has been unlearned, right? If the record is not successfully unlearned, the MIA signal of this record will be still very high. If it's successfully unlearned, when we perform the MIA attack, it will give us a very low signal. We would probably say it's a non-member. If it's detected as a non-member, that means it's successfully unlearned. So that's how we can actually use the membership inference attack to do empirical verification of unlearning. And finally, there's also work that trying to show a mathematical guarantee of the unlearning. So that is very actually similar or related to the differential privacy, somewhat like a certified unlearning, which shows a probabilistic guarantee similar to differential privacy, saying this unlearning has this guarantee. So that's for the unlearning efficacy. And finally, we also want to show the unlearning algorithm is efficient, because if we retrain a model from scratch, it does complete unlearning, but it's not efficient. So we want our unlearning model to be efficient, which means it should be much, much faster than retraining the model. Okay, so those are the goals or criteria we're going to use to evaluate our unlearning algorithm. What I want to show you is, first, this is kind of the seminal work that introduced machine unlearning. And this one is actually very simple. What it does is to say, okay, if we retrain the entire model, it's going to be expensive, right? So what is the simplest or the most straightforward idea to retrain a model without retraining the entire model over the entire set of data? So the simplest idea is to just split the data into multiple partitions, right, using sharding. So we can split the data into multiple shards, and then for each shard, we can train a model. And then the final model will be a simple aggregation of all the smaller models on the different shards. Right? And later on, if there is a record that requested to be removed, and if that record belongs to this shard, then we can simply retrain this model and then aggregate the entire models. Right? So that is the first work that introduces machine learning using sharding technique. It's a very simple idea, and it actually does the unlearning in an exact way. So that's why we call it exact unlearning. But then, of course, the drawback or the potential limitation is this: retraining this shard model is still expensive, right? Depending on the partitioning of the shards. And also, the final model aggregation of different shards may not perform as well as training the model on the entire data set, right? So that's the limitation of this exact unlearning. So people usually don't use this exact unlearning. Instead, people use, so I'll just skip this experiment. So people actually use approximate unlearning, which means we may not be able to guarantee the record is completely removed or by the retraining, but as long as we can show empirically it does the unlearning in a sufficient extent, then we're okay. So that's what approximate unlearning is. So what we did recently is did a contrastive unlearning approach following the direction of approximate unlearning. So in terms of approximate unlearning, there are mainly two techniques. So one thing is we want to unlearn the record. So what is the most intuitive way to unlearn a record? So when we do learning on a record, we do gradient descent, right? So we're trying to minimize the loss on all the records. So if we want to unlearn a record, what would be the most intuitive way to do the opposite of learning? Exactly, minus gradient or gradient ascent, right? So we just do the opposite of learning. Instead of doing gradient descent, we do gradient ascent. So that is the most commonly or one of the commonly used technique. When we want to do the unlearning, we perform gradient ascent on the forget records. However, this kind of approach may not be effective because it does not do the unlearning sufficiently either, or it hurts the performance because we don't really know how much ascent we're going to do. And another alternative approach is that instead of doing gradient ascent on the forget records, we can actually take the remaining records and do more fine-tuning, do more learning on the remaining records. So the rationale behind this is that a lot of times we do the model training, there's catastrophic forgetting, right? When you keep doing learning on the new records, you kind of forget the old records. So that is the property that this kind of approach is taking advantage of, is leveraging this forgetting quality of the models. When we keep doing fine-tuning on the new records or the remaining records, we kind of forget the old records. But however, as we can see, it may not be sufficient because it does not completely remove the influence of the old records. So either of these approach, they may not be sufficient, but these are the kind of commonly straightforward, intuitive approaches. So what we actually recently did is something called contrastive unlearning. Our main intuition or rationale is that instead of looking at just input-output space, we can look at the representation space. And that way, maybe we're able to do more effective unlearning. So the idea is, if we look at these data records, so if we illustrate or show their embedding in the representation space, right, after the model is trained, if we plot their embedding in the embedding space, so here we can see they're kind of clustered within their classes. This has been empirically shown by previous work, right? All the records that belong to the same class, their embeddings in the representation space are kind of close to each other. They're kind of clustered into their own clusters. So these corresponding to the 3 clusters, and these are the decision boundaries, right? So in general, if a record is in the training data, they will be closely clustered into their cluster. And if a record is a test record, meaning the model has not seen the record probably will be closer to the decision boundary. So the model will be probably still make a correct prediction on these new records, but it will be less confident. And similar insight as we have learned earlier, right? For the member versus non-member, the member will be very far away from the decision boundary, so the model is very confident. And the test record or non-members will be very close to decision boundaries, so the model is less confident. And now our goal is, given some records, we want to unlearn them. That means we want to make them as close or as similar to the test record or non-member data as possible. And in other words, we want to push them towards the decision boundaries, closer to the decision boundaries, so that they act similarly to the test record or the non-member record. So that's what we're actually doing. So we're just using the contrastive learning idea, but do it in the opposite way. Instead of doing contrastive learning, we're doing contrastive unlearning here, essentially taking some records. So suppose we want to, supposedly we want to, for example, unlearn this red dots here. So we want to pull them away or push them away from the records belonging to the same class, right? So that they are moving towards the decision boundary. So these we consider as positive pairs, right? In the typical contrastive learning, we want to push them together. But in this case, we're doing the opposite. For the neighbors or the records that belong to the same class, we want to push them away. And then for the, so push them away. And then for the records that belong to the different class, we actually want to pull them closer to those records that belong to the different class. So again, we're push them or pull them towards the decision boundary. So by doing these two things simultaneously, we're able to move this record closer to the decision boundary, acting more like non-member record. So achieving the unlearning purpose. So that's the main idea behind our contrastive unlearning algorithm. So these are just some, oops. These are just some illustration. And then another potential thing we did is that by pushing this away, because this is contrastive unlearning, so we may actually push these records away as well. So we maybe change their embeddings. So that would affect the performance or model utility. So in order to preserve the model utility, we're also using a auxiliary cross-entropy loss so that we maintain the embedding of these remaining records so that we both do the unlearning and maintain the model utility at the same time. So that's the main idea behind this. So this is the main loss. So this is the contrastive loss based on the negative pairs and the positive pairs of the records, and then with a additional classification loss. So quickly, I just want to show you some results. So these are different data sets, and turns out this kind of technique can be applied both in terms of classification models and also vision language models, like in general case.
Still can't understand how to do that. I mean, you're working just in the backbone. Yes, backbone of the model.
Yes.
Not the whole model. I mean, the representation side of the model, right?
Yes. So the optimization is, but we still update the model parameters. So the loss is based on the representation. Right? Yeah. So this is the loss. So the Z is the embedding, for example, the output of the last layer of the model. Yeah, so we are actually update our model parameters in such a way to actually optimize this contrastive unlearning loss. Basically, for each of the record, for example, ZI is a unlearning record that we want to forget. And ZA, for example, is the neighbors of this Z that have the same class label. And then the negative pairs would be the records that have different label. So basically this loss help us to make the embedding of this forget record closer to the neighbors that have different class label, but the neighbors that have the same label, it will push them away. So this basically is maximize this similarity or distance and then minimize this distance right here. So this is like a dot product, it's like a similarity. Does that make sense?
We are changing the loss function.
We're changing the loss function, exactly. So basically we take a model and then we retrain the model using, for example, all the unlearning or forget records and some samples from the remaining records as their contrastive pairs. So basically re-optimizing the model in such a way that these unlearning records are pushed away from their own class and pull closer to different classes. So it's kind of like the opposite of the contrastive learning.
So you are trying to make the confidence level for this.
Exactly. Yeah. Kind of so that now they are kind of mixed up in the middle, right? Instead of belonging to this cluster that the model has very high confidence of classifying them, now we're actually pushing them towards the boundary because they're further away from their own class, but closer to the different classes. And there's a very tricky part is where do we stop? So we did actually come up with a good termination condition to help us decide when to terminate. Because if you push them too further away, they'll be misclassified as a different class. Right? That also gives a negative signal in terms of membership inference. Instead of achieving the complete unlearning, you're pushing it too far away. So there's a tricky termination condition that we need in order to do the proper unlearning. Does that make sense?
Yes.
Okay. Yes.
And also the difficulty of pushing one unlearning sample might be different. Like someone may be in the middle of the cluster, and someone may be already very far from the center of the cluster.
That's very true. That's very true. Yeah. So we don't do so. This loss we are using here basically is a aggregated loss. So we don't do per sample calibration, and our termination condition is also an aggregated termination condition based on the accuracy of, for example, evaluation data set. Essentially, our goal is to make sure they're unlearned after the unlearning. The model accuracy on the unlearned samples should be similar to the test accuracy. So that means the unlearned sample should act the same as a test sample. So that was our stop condition or termination condition. But again, as you mentioned, that's still based on a whole set of the unlearning sample and the evaluation data set. So maybe there's certain samples are unlearned better versus other samples are unlearned less well. Yeah, so there are cases like that. So when we do the membership inference as verification, we actually can observe some samples are unlearned better. Some samples still have a membership inference attack risk. Yeah, great question. Yeah.
So you are doing this shift on the representative points of the clusters?
We are doing this shift of the unlearned records, meaning the records we want to forget.
So per sample or per representative point?
Per sample, yeah. So the dots here, each of these dots corresponds to a sample. So if we want to unlearn one sample, we take the sample and then take some neighbors as contrastive pairs, and then we just push the embedding away from these samples. Yeah. So this loss is basically an aggregation. Oops, sorry. So this loss is basic aggregation over all the unlearned samples. For each sample, there's some contrastive loss with the respective neighbors, and then we just aggregate over all the forget samples. Great. Okay, so this just shows you some result. comparing the contrastive unlearning with some other techniques, including fine-tuning, gradient ascent, and some other more state-of-art baselines, like knowledge distillation base and so on and so forth. So basically, this shows that our accuracy, model utility, both model utility and unlearning efficacy is stronger than the baselines. And coming back to our also efficiency, so this is the efficiency in terms of the time that it takes to do the unlearning. So it turns out this contrastive unlearning approach is also more efficient because it only needs to use several pairs to do the contrastive unlearning. And so we did this for class-based unlearning and sample-based unlearning. I'll skip this. What I want to show you here is that coming back to the MIA attack we have learned in the first part of the lecture. So here we can actually use MIA to verify whether these samples are actually successfully unlearned, right? So we take these samples we need to unlearn, and then we perform the MIA, and then we look at the positive prediction rate to see whether they can be positively predicted as a member. And turns out for our records, for our approach, the prediction rate is actually much better or stronger than the other approaches. But on the other hand, we can see it's not close to 100% or 50% AUC. That means either because the MIA is weak or because the unlearning is not done successfully. So in this case, our explanation is that the MIA attack is not strong enough. So it does make mistakes, even though we showed previously by the unlearning accuracy or by the test accuracy, it does perform very similar to the test data, but the MIA actually does not show complete removal. That just means the MIA itself may not be strong or powerful enough. Okay, so that hopefully gives you some idea how we can actually do unlearning of a sample from a typical model. And now I want to briefly show you how we can do unlearning on LLMs. Right? So that is actually a much more difficult and less well-defined task. Because for typical classification model-based unlearning, we're just unlearn, for example, one image or one record. Now for LLMs, what do we mean by unlearning? Can we unlearn a record? Can we unlearn a concept? Right? So that's very well, less well-defined. So I'll just show you one representative work on unlearning LLMs. And there are a lot of works going on and a lot of active research going on. So this work is one of the representative work that first introduced LLM unlearning. So basic idea or problem it's addressing here is that who's Harry Potter? Approximate unlearning LLMs. So it's based on the motivation that maybe the model is trained on copyrighted books, like a Harry Potter book. Now I want to unlearn the entire Harry Potter book collection from this pre-trained model. So the goal is so that when we ask anything related to Harry Potter to this model, to the unlearned model, the model should not answer anything intelligent or related to the real Harry Potter book. So here's the illustration, right? If I ask who's Harry Potter, and before the unlearning, the model would say, okay, Harry Potter is the main protagonist in J.K. Rowling's series of fantasy novels and so on. And then if we do the unlearning, hopefully the model would return something that's either very generic or not related to Harry Potter. So if a model is successfully unlearned, right? So that's the goal of this work. We're trying to unlearn this Harry Potter book collection from this model. So what can we do? What are the techniques we can use to unlearn these? So from the baselines we have learned so far, what can we do? Huh? Membership inference? Okay, so that can be used to audit or to verify whether that sentence is part of the training data or part of the model. Yeah, so that can be used as a verification. So how do we do the unlearn? How can we actually update our model so that it forgets this Harry Potter? DPSGD, okay, that's a good idea. DPSGD actually protects the privacy of the, it can achieve certain level. So we can actually fine tune our model using the, for example, Harry Potter collection and using DPSGD. It can probably add some noise, but it does not directly forget the content that's already learned in the model. Right? So what else have we talked about? The very naive, straightforward approach. Instead of doing, huh? Retrain the model. without the Harry Potter, but that's going to be very infeasible. We don't really know the large collection that's used to train a model, right? Yeah. Inverse of loss function, exactly. We can do gradient ascent, right? So how about we just perform the naive gradient ascent on a model using the Harry Potter collection, right? So there are some sentences from the Harry Potter collection. So we use this next token prediction. And in this case, maybe given the Harry Potter's two best friends are, given this prefix, the next token that has the highest probability is wrong. That's the model before the unlearning, right? Now we want the model to forget wrong. So we can do gradient ascent. So then maybe it will actually it will not output it wrong as the most probable token, but maybe it still remembers Hermione because that's the next likely token, right? So it still reveals some information. So by doing this gradient ascent, it may not do complete unlearning. So we need a stronger way to do this. So what the idea of this paper is that instead of doing the gradient ascent, we want to pick some token that's generic so that we can use it to replace this one. So what it does, the basic idea is that I'm going to take this pre-trained model and I'm going to reinforce it with the Harry Potter data. Just basically fine-tune the model, use this Harry Potter data, and then I have a reinforced model. So the idea is that now the reinforced model is going to really, really remember the Harry Potter information, right? And then if I take the output of the pre-trained model and the reinforced model, and I take their difference, if the difference is small, that means this token is very generic, right? If the difference is high, that means the token is very specific to the Harry Potter collection, right? Because this is a model that's reinforced using the Harry Potter collection, and this is the pre-trained or whatever model. So if the difference is small, that means it's a generic token. So I'm going to use this generic token as a replacement of the original token. So that's what the idea of this paper is. By taking this, it actually does a kind of forget data set, and then use this forget data set to fine-tune the model, and so that it hopefully answers some generic token instead of Harry Potter. Yeah.
Do you know if this is also resilient towards attacks where you take like the general sentence and then you just shuffle the words?
Yes, that's a good idea. So you can shuffle the words. However, that would potentially ruin the utility of the model, right? So you still want to preserve the utility of the model, meaning it would generate coherent sentences. You don't want to generate like a gibberish.
I'm not talking about like doing that with the RL. I'm talking about doing that to an attack. Like if I do that, let's say swap around the tokens.
Yeah, I see.
The model is still resilient towards extraction from those things.
That's a good question. Actually, I haven't tried.
I think it's still like would remember certain patterns.
It would probably remember something, yeah. So again, these are not these are approximate unlearning, so it does not guarantee any unlearning. So there could be ways of kind of escaping the unlearning by switching the order of the token. It's kind of like a jailbreaking, right? You come up with kind of different prompts.
There's also this paper by Matilda and some others, even if you do like alignment, you can, it still is like mostly along one dimension.
Right.
You can do unlearning against on that.
Right.
And then uncensored.
Right.
So I guess this would sort of.
I think so. Yeah, I think so. I agree. Yeah. So it is a kind of a difficult task. Also, there's been showing that models that are unlearned this way is very easy to be relearned. So if you try to unlearn the model, for example, 100 samples, unlearn 100 samples, or unlearn this entire Harry Potter collection using all the sentences to unlearn the model, and later on, you can actually relearn the model very quickly by using a very small subset of the unlearned data. It just means this unlearning is actually kind of fragile because in the kind of lost landscape, maybe this is the model, the optimal model. And once you unlearn it, it maybe moved it to some, for example, other point, but it's still actually kind of close to the original optimal point. So it's very easy to actually relearn it back. It's not very robust, a lot of these techniques. Yeah.
You also comment a little bit about the catastrophe forget.
Yeah, so the catastrophic forgetting is one way to do this unlearning, but it's not, again, not very robust, or there's not a stronger guarantee, right? So you can do this fine tuning and all that, and there is catastrophic forgetting of the previous records or the records that are not being used for this fine tuning, but there's never a guarantee. Also, if those records are kind of similar to the fine tuning records, they're still being remembered. Yeah, but that is one property, yeah, people have been leveraged to do the unlearning. Yeah. Okay, so I think we're out of time. So so they showed some experiments and basically, yeah, doing more epochs, you were able to forget some of these content and so on. And then they also showed it still performs reasonably well for the other data sets or other benchmark data sets. So the model utility is somewhat maintained. Okay, so I think that concludes all the detailed stuff that I'm going to talk about. So I'll just use the the extra 2 minutes to talk about some of the open challenges, right? So far, what we mainly focused on as a privacy enhancing technology or attack is on the training data. Right, so the training data is used to train a model. We're trying to do the membership inference or data extraction of the training data. And then all our techniques are focused on these 3 different stages: pre-training, during training, and after training. But turns out when we are now in this LLM era, the landscape is actually much, much more complicated than our typical AI model pipeline, right? So we have the pre-training stage, and then we have the fine-tuning stage, and we also have the alignment stage where the models are aligned for safety reasons, for privacy reasons, using different preference data, human feedback data, and so on. And then post-training, there's in-context learning, right? We don't do fine-tuning anymore. We do in-context learning, provide demonstrations, and provide the chain of thoughts and ask the model to do in-context learning. And finally, there's also model collaboration, like retrieval augmented generation and knowledge database distillation, and so on and so forth. So all of these, so far, we only focused on one very small region of this. We're trying to protect the domain data that's used for fine-tune or train a model. But in fact, in this entire ecosystem, there's privacy challenges associated with the data, generic data for pre-trained model, the domain-specific data for fine-tuning the model, also the preference data for aligning the model, and also even post-training, there's context data, demonstrations used to do the in-context learning, and knowledge databases used for doing these model collaboration or RAG and so on. So all of these actually have privacy concerns. So there are some work that started looking at, for example, RAG or in-context learning, what are the privacy risks associated with these context data and knowledge data, and MIA on those in-context learning, and some DP techniques in terms of protecting this context data and knowledge data and so on. So there are a lot of open issues here. So I hope that gives you some thoughts, some things to think about. And as you build your own solutions, these are the potential vulnerabilities, and there are potential techniques, and people are actually working on them to kind of address and mitigate these privacy risks so that we move towards building more trustworthy AI solutions. Okay. So with that, thank you.
No, so then we can have a break now, and next